Okay, welcome to everybody to the last day of our conference. It's for several reasons my great pleasure to introduce the first speaker today, my dear friend and colleague, Dr. Vishvesh Kumar. Let me just say a couple of things about Vishvesh. Vishvesh got his PhD in 2019 from the Department of Mathematics and the Indian Institute of Technology in Delhi. And from May of 2019, and from 2019, he is a member of the Ghent Analysis and PD Center, where he is associate researcher, senior associate researcher. So today, the talk of Professor Vishvesh Kumar will be about hypoelliptic damped wave equations on Great-Delhi groups with initial data from negative order Sobolev spaces. So thank you very much, Vishvesh, for accepting our invitation. It's my great honor to have you today here. Thank you.
Okay, thank you, Duan. So first of all, I would like to thank all the organizers of this wonderful conference. And today I will talk about hypoelliptic damped wave equation on Great-Delhi groups, and specifically considering initial data from negative order Sobolev spaces. So this is the joint work with several people. So Prajita Dasgupta and Syam Sarup Mandal from India, and Michael Rojansky and Berik Bolto-Rebek from our Analysis and PT Center. So these are the three papers this talk will be based on. Specifically, this talk will be based on last two paper, which actually first two paper is kind of particular case of the second paper. So let's begin. So aim of our this talk to understand the equation 1, which is damp wave equation with a Rockland operator, which is R is the Rockland operator with homogeneous degree nu, which is supposedly is greater or equal to 2 on a graded Lie group G. And so this equation is wave equation with a damping term ut and with power type non-linearity. And initial data is taken from negative order subgroup spaces, homogeneous subgroup spaces, and epsilon is here size parameter to control the size of the initial data. So our aim is to study here this global Belpogeness and other property of solution of this equation. So let me put, I will explain all these term, Rockland operator, graded Lie group, and other things in this scenario, in this talk. So let me put first some context of the examples where people may not be familiar with Lie groups, anything. So here, the example of graded Lie groups, you can consider first thing is just abelian group of Euclidean space. Or if you know the non-commutative, you can consider Heisenberg group, other nilpotent Lie groups, and more generally, like very important Lie groups, which are stratified Lie group, are example of this these graded Lie groups. And for the Rockland operator, particularly in Euclidean space, you can consider any power of your positive with positive and negative sign of the Laplacian power. So in particular, your Laplace-Beltrami operator or R is a Rockland operator. But here you can consider here, like suppose m equal to 2, and you can think like our result in this setup. So if you don't know about Lie group or Lie algebra, which I will actually not explaining here because of time constraint. So particularly you can consider everything G is like Rn and this Rockland operator R as power of Laplacian. Okay, and you can consider this kind of operator as well here in commutator setup. And there are several other examples which I present. So as we need to explain the study the solution of this equation, so let us discuss what does it mean by solution of equation. So let us consider this damp wave equation with inhomogeneous damp wave equation, and by using Duhamel principle, you can write the solution using this integral equation, and where this E1 and E2 are the fundamental solution with initial data given by this Dirac delta function at 0. And then once you have this integral representation, then we can define what is known as mild solution of this equation given by a fixed point of this integral on a space which is called energy evolution space, which we need to define suitable energy evolution space, and such a fixed point is called mild solution of this damp wave equation. And then I'll define a more general solution which is called weak solution. So weak solution is a solution which is on LP log of this space which satisfy this property. So which satisfy this integral relation which you can get by integration by part. And if this time t is infinite, then we call this weak solution is global, or otherwise we call it local solution. And in particular, it's interesting to note that every mild solution is also a weak solution. Now, we will also discuss some blow up in time solutions. So particularly, we say that a solution of this damp wave equation blow up in finite time if there exists a time t, such that the infinite norm of this UTM goes to infinity if Tm goes to infinity. And then based on this, because time now blow up, solution has this blow up behavior. Once you have, then you can also define a lifespan of this. So lifespan is the maximal time existence for the solution of this damp wave equation, which is informally given by this definition. Okay, so now we have know that what is a notion of the solution, and so let's discuss some result in Euclidean setup, first literature. So in this case, is our group is just Euclidean group, and then our Rockland operator is just minus Laplacian. So in this setup, this is the setting. So first result was by Matsumura, where they consider initial data, positive initial data, and also consider that these initial data belongs to L1 of R. Then Matsumura, he proved that global in time existence for a small data solution for P bigger than this number. So, and then later on for higher dimension, Todorova and Yozono, they proved the global existence data, global existence of the solution, especially mild solution, but they put condition that initial data is compactly supported. And blow up part, they prove that blow up of the local time in solution for the P less than this number. Okay, so in particular, you can see the behavior of the solution is depending upon this number. So on at P equal to this number, this exponent for this, Zhang explored this problem and proved that at P equal to this, also solution belongs to the blow up region. And later on, Ikehata and Tanijawa, they removed this compactly supported condition from this result of Todorova and Yozono. So you can see this exponent 1 plus 2 over n play a very important role in the classification of the solution, like where solution has global existence or is blow up. So that's why it's called a critical exponent. So based on that, now later on several people study sharp lifespan estimate, which are given by this. So of course, when P is greater than this critical exponent, then solution of critical case. So when P is less than critical, we call subcritical case is given by this this quantity depending upon the size parameter of the initial data. Now we can notice that this critical exponent is playing the same role as in the damp wave equation setup, which was played the same role in the setup of semi-linear heat equation with some suitable initial data, of course. And this study was for heat equation. It was done by several people. It started with the Fujita, Hayakawa, and Wessler. They proved that this exactly same exponent was playing this role of the critical exponent, and that's why it's called now Fujita exponent. And then later on, several people actually discovered that indeed the asymptotic behavior of this damp wave equation is similar to the behavior of the heat equation with some nice initial data, and that's what is nowadays called as diffusion phenomena of this damp wave equation. Okay, so now let us move on from L1 data to some other space data. So till now we were talking about only L1 data. Now let's move to LM data. So now we are considering instead of L1 initial data from LM, where M belongs to 1 and 2. So in this case, people Ikehata and Ohta and other people, they found that Fujita exponent was, or critical exponent was given by this number. So where 1 plus 2 m upon n. So m appear here. So m equal to 1 is just Fujita exponent. But it was very interesting to note that in contrast to L1 case, it was observed that when on the when p equal to Fujita exponent on this case, then actually your solution belongs to global existence result with small data. Okay, so this was the very interesting phenomena here. So now you can notice easily one can notice using Sobolev inequality that LM is contained inside homogeneous Sobolev spaces of negative order with gamma given by this. Then it's natural to consider this damp wave equation with the solution on more general or bigger space from bigger space that LM, that is here negative order Sobolev spaces, and that was the case. Chen and Reisig, they consider this damp wave equation with negative order Sobolev spaces, and it was not the first time when people consider this kind of data. Actually, this was already done by several people, particularly by these two papers, which discuss Navier-Stokes equation and Boltzmann equation from data with negative order Sobolev spaces. So what Chen and Reisig they did, so they discovered that in this setup, when you take initial data from negative order Sobolev spaces, the critical exponent changes and it's given by this 1 plus 4 upon n plus 2 gamma. So particularly when your gamma will be 0, it go to L2 data actually. Eventually, if it go gamma go to 0, and then they prove that when for supercritical case, the problem 11 has admit a global in time solution for small data, and then for the subcritical case, they prove that the solution blow up, and for the critical case, it was left as an open problem here, and then very recently, Debico he proved that critical case belongs to the small data global existence. Okay, so this was the condition like literature till now. Of course, there are several like infinity many paper on this whole literature. I can't present here all of them, but this was the concise review, and you can find more references in these mentioned papers. So now let us discuss our setup. So in our setup, we want to deal with graded Lie groups. So let me introduce first what is homogeneous Lie groups. So simply connected Lie group G with a topological dimension n is called homogeneous Lie group if it's Lie algebra, which is actually as a vector space, finite dimensional vector space is isomorphic to Rn, is endowed with a family of dilations, which are nothing but vector space automorphism satisfying these two properties. So first is property that this map is of this form, and for where A is some diagonal of matrix on G, and then second is satisfy this Lie bracket condition. Okay, so it's actually Lie algebra morphism here, and then secondly, this way, this eigenvalue of this operator A are called dilations weight, and associated with these dilation structure or dilations, there is a new quantity called homogeneous dimension of these homogeneous Lie groups, which is given by the trace of this dilation matrix. So it is just nothing but nu one plus nu two up to nu n, and indeed you can just jointly rescale this value and make it like nu one is 1, and then what you can see easily that homogeneous dimension are always bigger or equal to topological dimension, and this homogeneous dimension play a very important role in this analysis on homogeneous Lie groups. So once you have this dilation, then it's known that this dilation with group with dilation are immediately are nilpotent, and these dilation on Lie algebra actually induce a family of dilation using exponential map on these Lie groups to a dilation on Lie group where and those Lie group are called actually homogeneous Lie group. Indeed, one can consider here Haar major. Every Lie group has a Haar major. So here this is just nothing but a Lebesgue measure on Rn, but this is homogeneous with respect to this homogeneous dimension. So that's also very important to note here. Okay? And everything about homogeneous Lie group could be found in the seminal book by Poland and Stein, and they introduced these really homogeneous groups. So now let us come to graded Lie groups. So graded Lie group G is connected, simply connected Lie group. Lie algebra is graded in the sense that you can write it as a direct sum of Gij, so that it satisfies Gij bracket of Gj is coming Gij plus 1, and also is if Gij plus 1 is 0, if I plus j is greater than s. Okay? And these gradation give a natural dilation structure on this group using this. So you can define a dilation matrix on this, and that actually come to the dilation of this group. So that means every graded Lie group is a homogeneous Lie group. And then particularly interesting for several people or in analysis or in geometry are stratified Lie group, which are defined using if this algebra is stratifiable. That means if there exists a gradation G such that this whole Lie algebra is generated by G1. So G1 and Lie bracket with Gi commutator with Gi plus 1 for all I. And such a Lie group associated with such a Lie algebra is called stratified Lie group. So particularly, I will explain what is Heisenberg group. So Euclidean and Heisenberg group are particular case of stratified Lie group, which are in graded Lie group. So we are doing analysis here, and you will see why we are doing analysis on graded Lie group, not on homogeneous Lie group in general or to general nilpotent Lie groups. Okay, and everything about graded Lie group you can find out in this monograph by Fischer and Lujansky, quantization of nilpotent Lie groups. So now let us present some example of the graded Lie group. So first thing is I already told you that abelian group, so Rn plus our usual plus operation. So here the Lie algebra is just trivial, and dilation you can know the dilation on R, that is each component is the same dilation, so it's isotropic dilations. But you can change the dilation structure on R also. So if you define your dilation like this, then if still and where nu1 nu2 are rational, then Rn with this family of anisotropic dilation is also has a graded structure. Okay, so now we now move to non-commutator setup. So first, one of the important example of a non-commutative graded Lie group is the Heisenberg group, which is used in several mathematical physics and other branches of mathematics. So here, as a topological space is just R2n plus 1, but a group operation is different than R2. That's the usual group operation on R2n. So here you can see that first two components are same as a usual operation on R2n, but the third component is bit different, and because of this of group operation is non-commutative. Okay, so this is non-commutative Lie group, and canonical basis for the Lie algebra of this group is given by the vector field, where this vector field satisfies this commutation relation. And indeed, you can define dilation on this Lie group by this. So here you can see dilation are defined in different way other than Rn. So here first two components are scaled by just R, and then last component is scaled by R square. Okay, so these are the two examples which you can keep in mind. So now let me define a general Fourier analysis on graded Lie group. So first, let us denote G hat as the unitary dual of G, that is set of equivalence classes of strongly continuous unitary irreducible representation of this Lie group. And based on that, we can define Fourier transform. Fourier transform here at any representation here from representation space, which is Hilbert space H pi to H pi, is an operator in general because these are operators. So it's given by this 13. Okay? And then once we have these, then actually there's just a measure on G hat such that we can recover F from its Fourier transform, that is in Fourier inversion formula. And indeed, like in Euclidean case, in Fourier transform, in Euclidean case, we have here Planck-Charrer identity. So the following Planck-Charrer identity hold here because this Fourier transform at any point pi, which is representation, is an operator. So these are nothing but Hilbert Smith operator. So we need to take Hilbert Smith norm here. And this Fourier transform extend uniquely to the unitary isomorphism from L2 to L2G hat. Okay. Now, let me discuss what is Roch-Lund operator. So let us first set a notation. So for any left invariant operator T, so that means this belongs to universal enveloping algebra of Lie algebra Z, and we denote pi of T as a symbol. We call it symbol of T, which is nothing but infinitesimal representation denoted by d pi T associated with a representation of G. Okay. Now a Roch-Lund operator. So what is Roch-Lund operator? So Roch-Lund operator is a left invariant differential operator on R on a homogeneous Lie group, which is of positive, which is homogeneous of positive degree nu. That means this identity satisfies. So you dilate a function by this dilation, and this R power nu comes up. Okay, with comparison with the dilation. And this operator, which is symbol of this Roch-Lund operator, is injective on the smooth section of the smooth vector of this representation space. So that means what? That when pi of R apply on V is 0, this implies that V is 0. And then this condition is called Roch-Lund condition. And in fact, this Roch-Lund condition is equivalent to the hyperellipticity of this Roch-Lund operator. That means if you have Rf belong distribution, any distributional solution, Rf is C infinity locally, if this implies that F is also in C infinity. Okay? And indeed, it is known that if you have a Rockland operator on a homogeneous Lie group, then it automatically implies that G is graded Lie group, and that is the exact reason we are dealing here with a graded Lie group. So because we are here in Rockland condition, Rockland dealing with Rockland operator, so we are forced to deal with in graded analysis on the graded Lie group. Okay, and of course on graded Lie group you can define a Rockland operator. So now let me discuss some more analysis about this Rockland operator. So if you apply Fourier transform on the F, then you get symbol of this Rockland operator, and then F apply on this. So this is called symbol of Rockland operator. If you understand this kind of Fourier multiplier with symbol pi of r, and in general this pi of r, this spectrum is discrete and is positive spectrum, and that's why it's even self-adjoint. Then you can write this, you can choose the orthogonal basis and write this pi r as a infinite dimension matrix which is divisible in this. Okay. Now let me define Sobolev spaces. So Sobolev spaces, in particular, this first inhomogeneous Sobolev spaces are defined using same definition, but instead of Laplacian, we have replaced here Rockland operator with this mu here. So which is homogeneous degree of this Rockland operator, and these are given by this norm here. And same way you can define homogeneous Sobolev spaces. And indeed, you may be wondering that if we choose the Rockland operator on a grid on a graded Lie group, then maybe these Sobolev spaces are dependent on this Rockland operator, but in fact this is not the case. So these Sobolev spaces are independent of the choice of Rockland operator, and you can find all about these Sobolev spaces by this paper of Fischer and Rózsánszky. So now let me show some inequality which are very useful in our setup. First is Sobolev inequality. So this is the Sobolev inequality on graded Lie group, and second is this interpolation inequality or Gagliardo-Nuremberg Sobolev inequality, which is given by this inequality 17. Okay, so these are very useful when studying this damped wave equation, and you can find this inequality in the same paper of Fischer and Rózsánszky and other paper by Rózsánszky and Tuchman. So now finally let me discuss some examples of Rockland operator. So for on any graded Lie group, you can consider this sum of this vector field with some power of this dilation weight, and which is Rockland operator of homogeneous degree 2 nu naught. Okay, and secondly, if you consider a stratified Lie group, so that this first is strata of your Lie algebra generate the whole Lie algebra. In this setup, you can consider this sum of square, which is basis of first stratum, xi up to x, and this is actually called sub-Laplacian, is a hypoelliptic operator satisfy Hormander rank condition. So this is also example of a Rockland operator. Then particularly on Heisenberg group, because that's a part of stratified Lie group, the sub-Laplacian and its any power are also Rockland operator. On Euclidean space, of course, you can consider power of Laplacian, but you can consider these kind of operator as well. Okay? So particularly, you can see that in our setup, all these examples are included. So we are dealing with much more general setup, but these results are also even new. For example, on stratified Lie groups, or even for power of sub-Laplacian on Heisenberg group, or power of Laplacian on Rn. So let me discuss briefly about a damped wave equation on Lie group setup. So particularly on Heisenberg group. So first result for wave equation, let me mention this famous paper of Muller and Stein. So they estimated LP estimate of the wave equation. Then for the heat equation, actually because heat equation is very much related to the damped wave equation, so let me tell. So briefly, heat equation first time was studied by Pascucci and Zhang. At the same time, And they found out the critical exponent of the same linear heat equation is given by 1 plus 2 upon q, where q is the homogeneous dimension. So you remember that in Euclidean space it was given by 1 plus 2 upon n, and here is just 1 upon 2, 2 by q. So in Euclidean space, q is nothing but topological dimension. My group is abelian, but in Heisenberg group, this q is different than topological dimension because topological dimension was 2n plus 1. So this homogeneous dimension is playing an important role to study the heat equation on Heisenberg group. Then let me mention a result of Ruzhansky and Tukma-Gambatev, where they consider damp wave equation with mass term. So here they put this mass term. So on this case, they prove global existence case. Because of this mass term, they get exponential decay, and they prove, and then other result by Ruzhansky and Taranto for time-dependent coefficient. Recently, Ruzhansky and J. Serkegno, they consider this heat equation for a general polynomial growth group, and they found out that 1 plus 2 upon d is actually Fujita exponent in this setup, where this d is the global dimension of this group. In 2019, Gargiu and Palmieri, they consider a damp wave equation on Heisenberg group with power type nonlinearity, of course, and they found out that what this Fujita exponent was discovered by Pascucci and Zahn, it was exactly the critical exponent for this semi-linear damp wave equation, and this is the same phenomena as in Euclidean space. And in fact, they prove global existence of small data solution and also blow up case. And Palmieri in 2020, he also proved this L2 decay of the solution of homogeneous damp wave equation. Okay, so now let me discuss our results in brief. So first thing is we consider a graded Lie group. So once we consider graded Lie group, then our dilation are fixed, and that's why homogeneous dimension Q are fixed. And then once on this graded Lie group, we consider a positive Rockland operator of homogeneous degree nu. And by taking initial data from negative order subspaces here, so here I didn't put G, but these are defined on, of course, on this graded Lie group G. Then solution of this linear Cauchy problem. So here is a homogeneous. Each have this HS homogeneous sublow decay of this type in 19. So you can see this gamma here appearing. So gamma is the order of this negative order sublow spaces here. So particularly this provide some kind of initial, some kind of actually extra decay of the solution when we consider data from initial data from negative order sublow spaces. Okay, suppose gamma is 0, then it's just from L2 data, and you can get don't get this in extra decay. Okay, and here then this theorem actually is nice in a way because you can get L2 LM decay in this setup. So L2 decay, and this theorem is in fact generalized or extend result of Palmieri, where he considered this damp wave estimate of this solution of linear damp wave equation for L1 data, okay, in the Heisenberg group setup. So here our setup is much more general. So here, in fact, you can consider any sub-Laplacian and consider this stratified Lie group, or consider here just Rn, here consider power of Laplacian, and then still this result are kind of new in this setup. Okay. So let me sketch the proof of this theorem, especially this theorem of this theorem, where we can say we have this sublow norm of the solution or decay, this sublow decay effect. So what we do, so we use group Fourier transform, so which is, you remember, is operator valued. So we apply group Fourier transform with respect to our group variable x, and we get this nice equation 21, and where this pi r is the symbol of Rockland operator. So in particular, if you consider actually like in Heisenberg group, then this symbol is the harmonic oscillator. So you can now relate maybe things better. So here, this is the symbol of Rocklin operator. And then we can, by introducing a new notation corresponding to the eigenbasis with which the symbol of the Rocklin operator has a diagonal label, is diagonal label, we can write this equation as a kind of infinite system of ordinary differential equation. So now we will convert to ordinary differential equation with this notation beta m pi square is pi m square. And now we will try to solve this. Okay, so the characteristic equation corresponding to this ODE is given by this, and once you solve it, then the characteristic root are given by this. So now it's actually depend upon the beta and pi, right? If they are kind of imaginary root, real root, or distinct, right? So now we have to put condition on beta and pi. So we'll consider three cases. So first case is given by this when beta and pi is very small, right, which is less than delta, or some delta very smaller than 1. And then in this case, the L1, lambda 1, lambda 2 are given by this asymptotically. And then here for large frequency, actually, is given by this. And when you consider middle frequency is given, is just, now we can notice the negative part of, real part of lambda 1, lambda 2 are negative. So particularly, you can in fact solve this equation, this homogeneous equation, this one is easy to check with this. And this is given by solution. Any solution of that could be written by this, where K0 and K1 are the kernel, actually, is given by this equation. So you can see it's 28. And by writing the value of lambda 1 and lambda 2 in every setup, you can see that this exactly given by this. So now, and K0 is given by this. So once to estimate this this term to solutions, we need to estimate these kernels first. Okay, and once we estimate this kernel, then we can apply this kernel estimate here to the estimate of this. Okay, so let's see first one. So the point-wise estimate of this K0 and K1 by using some nice calculations, you can get that when for low frequency part, you can see that this decay has this. In middle frequency also exponential decay, and also for low frequency is for high frequency is exponential decay. And here you can check also that they have decay like this. And then once you have this estimate of the kernel, then what we do, we use the Planck formula for the Fourier transform. So any Sobolev norm of this could be written as this with Hilbert symmetric norm. So this is just nothing but you apply here a Rocklin operator with the symbol of the Rocklin operator. You apply the Planck formula, you get this. And once you have this, then you can decompose it using the basis, and then you get this equation 24. Let's write it IK0 and IK1, where these are the K0 and K1 term. So now we need to estimate these IK0 and IK1. So for low frequency part, one can estimate this here. So in low frequency part, you can see this decay of this IK0 is polynomial. Here is polynomial, but for the high frequency part, this decay is exponential. So you can see the high frequency part is much more nicer. And then for the middle frequency part also is a exponential decay. So now we can combine all these three decay. So now we have here, so exponential decay. So of course exponential decay is nicer than polynomial. So when we want to estimate, we'll get polynomial decay only. So by putting all these things together, we get that HS norm of the solution is less or equal to this times 2 and with this initial data. And that's the proof of the theorem of our main theorem. Now, using this linear estimate of the solution, we prove our global existence. So first I consider here supercritical case. So that means this is our exponent here. So this is the critical exponent, so 1 plus 2 nu. So here you can see that this nu is the homogeneous degree of Rockland operator, and q is the homogeneous dimension of graded Lie group. So now we consider p greater than this pre-critical, and it also depend upon this gamma tilde, which is positive root of this quadratic equation. And we consider initial data from negative order subwave spaces with this epsilon as a size parameter satisfying this. So data is very small here. So based on that, so we prove small data existence, global existence of the solution for this range of P. We need to put this technical thing due to some technical challenges here. But anyway, in this setup, we prove that the solution has this. So there exists a unique solution on this subglobe spaces. So we prove global existence of a small initial data solution to the damped wave equation. This, and in fact, one can also estimate any solution of this semi-linear damped wave equation, and see that they also have same decay as homogeneous one. So inhomogeneous and homogeneous have same decay, and that's very nice thing to see. Okay. Now here it was a supercritical case. So now we will consider critical case. So for the critical case, what? So here we consider critical case. So for the critical case, we consider we have to put several conditions based on the homogeneous dimension, and this we need to restrict the gamma. Okay. And then in this case also we prove that if you take small data, small initial data from negative order subglobe spaces, then there exists a unique subglobe solution of this damped wave equation earlier. Okay. So we prove that for supercritical and critical cases, our damped wave equation has a small data global solution. And what we use to prove this, we of course use group Fourier transforms on X variable on graded Lie group. Then we use subglobe estimate of the solution for the linear Cauchy problem, which we discussed. And then we use super inequality and Gallardo-Nirenberg inequality on graded Lie group. And using that, we proved existence of mild solution using the Banach-Fixed point theorem on appropriate energy evolution spaces. And some condition there. So you can see that this condition, now P, where we put this this condition, P is less or equal to Q upon Q minus 2S. This is coming from our application of Gallardo-Nirenberg inequality. One can improve it, but it's just this is technical. And in some cases, you can see the range of, because here you can consider which kind of P we can consider, which kind of operator we can consider here. What is, because it's too technical to see like this condition. But let me tell you that when you consider Q is equal to 1 and 2, so your group is just abelian in this setup, but you can consider new anything. So you can consider maybe power of Laplacian on R2. And then in this setup, actually you can see that this P satisfy this condition, and 3 and 4 you can see that this is the condition on P. So we have to consider this P. And in the subcritical case, so in subcritical case we prove blow up of the solution. So solution blow up in finite time, but for that we have to consider a particular class of the Rockland operator. So in this class, we consider this particular class of the Rockland operator on graded Lie group with homogeneous degree nu, and where this xi, xn are strong same basis. That means for any k less than n, any set of k vector from here or k vector field, generate an ideal of this Lie algebra. And then in the subcritical case, we prove that solution blow up on a small time. So there's no global solution for this damped wave equation. So particularly you can see here this diagram explaining several things. So for dimension 1 and 2, you can take new anything bigger than 2, and you can see that we know everything about it. So for this this range we have global existence, this range we have blow up. And then for this is for dimension homogeneous dimension 3, and then mu is equal to 2, we know these things. Then especially 5 for 5 6, you can see it's a bit technical, but we know specific ranges. And from the diagram also one can see that for 1 and 2 we know everything, like we know that this is the critical case. But for the 3 4 5 6, this range is kind of empty. Here we don't know how the solution behave, but one can see that this graph go below slowly once we increase this gamma. So it depend upon gamma. So but this is some kind of empty range. We don't know how to fill that, but at least we know that this is the graph which is critical exponent, which separating global existence and below. Okay. So now, because our solution blew up for the subcritical case, then what we did, we estimated the lifespan of that solution, and we get that for, of course, for p greater or equal to critical, which solution solution exists globally, lifespan is just infinite. But for the subcritical case, it is given by this number, and here c is of course independent of epsilon if you put c. Okay. Now, let us see, because earlier we discussed that this exponent when you consider damped wave equation with just L1 data, the exponent, the critical exponent was just Fujita exponent, and even many people proved that asymptotic behavior of damped wave equation, so solution of the damped wave equation is same as the heat equation. And what does it mean? What is called diffusion phenomena. So here we consider this heat equation with Rockland operator on the Rayleigh group, and we estimated this HS decay, HS norm of the solution of this homogeneous heat equation that is given by this decay. And also recall that for decay for the damped wave equation, HS norm of the solution of the damped wave equation has also same decay. You can see they have same decay, but if you compute here that the HS norm of the difference of solution, the damped wave equation and heat equation, then this has actually initial extra decay of this minus one extra decay, and that's why it's actually go to 0 if you have this and it's called this diffusion phenomena. So this is although the solution of each individual equation they have same decay, but when you actually try to compute the differences on the norm of the difference of two solution, it has extra decay, and this is called diffusion. So in particular, it confirmed that in our setup also, where you take initial data from negative order subgroup spaces, or you are working on Rayleigh group with Rockland operator, this diffusion phenomena continue to hold. Okay, so let's check our what we discussed. So in this talk, I discussed damped wave equation associated with Rockland operator of homogeneous degree nu, and on a graded Lie group G with homogeneous dimension Q. And what we found out, a critical exponent, and what that? This is given by this number. So for the subcritical case, the solution blew up, at least for the particular class of Rockland operator, and for the supercritical case and critical case, the solution has a global existence. So this was the motive of this talk. And some further direction, it will be nice to consider actually heat equation and non-linear heat equation, some linear heat equation, and then try to see how this global existence, and if this is the Fujita exponent actually. In fact, we don't know yet that is a Fujita exponent or not, but it will be nice to consider, and it will be, I think, very good to consider LPLQ decay. Here we only consider LML2 decay in a way, but here it will be nice to consider this in L2 LPLQ decay for solution of damped wave equation, or in fact for wave equation on the Rayleigh group, or particularly on a Heisenberg group. But I think this is very difficult question. So Thank you.
Okay. Okay, Vishwesh, thank you very much for your very nice talk. So it's time of questions. If someone has questions for Vishwesh, please do now. Maybe remember that you can make your question raising your hand. Maybe Vishwesh, I can start with one question.
Okay, please.
Thank you. In your model,
Yeah.
in your equation, right? You have your
Yeah,
wave equation.
Yeah. I can maybe open the wave equation.
Sorry, it was at the beginning, yes.
Yeah. I put here maybe this. Okay. Let's try to. Maybe it's a homogeneous.
Okay, yes. Okay, this one. Have you considered, or your analysis, do you think is can be adapted if you consider time dependent coefficients? Or
Indeed, it can be used actually like for time dependent coefficient as well. It's just suitable condition on the coefficient, and it can be used for time dependent coefficient, and I believe also for maybe non-linearity, which a derivative non-linearity with time, it could be used the same strategy. And
Okay.
these estimate will be useful actually to establish that.
Okay, that's my question, right? Because it's okay, it's suitable for your Fourier analysis, right? The Fourier analysis.
Yeah, indeed. If you have time dependent coefficient, it can be done, but if you have space dependent, no.
Okay.
No.
Okay. Okay. Space dependent is Fourier integral.
Yeah. Then we can.
Excellent. And maybe another question. Of course, I don't want to make technical questions, but when you do your Fourier analysis, you divide you divide the regions, right? The regions of the coefficient in. Could you please explain why you have to make this division in two or three regions of the unitary dual?
Yeah, actually, it's because of you see this behavior of lambda and lambda 2 are depend upon this behavior of the eigenvalue of this beta m actually. So that's why it's you see it has like which kind of solution it has, like it's given by sine and cosine, or it given by sine hyperbolic and cosine hyperbolic, right? So that's why it depend. So you need to divide it into three part in a way, or particularly you can see like or you can divide by beta when 1 minus beta 4 minus beta square is 0 or negative or positive. That's decide the behavior of this lambda and lambda 2, right? Like how these are, because then you can write your solution of this ODE in suitably in sine and cosine, or in fact you can see that when you are in high frequency, this behave like wave equation. Actually, when you are in low frequency, this behave like actually heat equation. It's kind of thing. So that's the behavior. So it's like hybrid actually behavior. It has from heat and wave both, and that's why we need to divide it. Yes.
Okay, very interesting, of course. Okay, does anyone have a question for Vishwesh? Okay, maybe I can make a last question. Okay. Maybe you can mention some open problems, Vishwesh.
That's the open problem I mentioned. See here at the last, I mentioned that to prove LP-LQ estimate for the solution of just linear wave equation or damped wave equation on Geddeley group or particular on Heisenberg group. Because for the wave equation, LP estimate was done by Stein and Muller, but then LP-LQ, no, nobody is a free integral operator. So I think it will be nice to study at least for damped wave equation LP-LQ. I have here, if you see this L2 LML2 estimate, but not for general LP-LQ, we don't know. So here you can see that we have estimate from LM to L2. So we consider initial data from, and then we have L2 with initial data. Of course, it's L2 L2 estimate with initial data on LM, but it will be nice to consider LP-LQ estimate here, and then one can do much more general analysis, I think, here. But just I think it will be very interesting.
Okay, maybe someone did a question. Tobias Castro, who say,
I cannot see actually. Can you read?
I can read, yes, I can read for you. You say, okay, you introduce an epsilon in your initial conditions. Could you please tell us a little bit more on the purpose and intention behind using that epsilon? Okay.
Okay, because usually we want to control the initial data. Okay, and that's the we want usually for, of course, you want to have a small initial data, and that's epsilon each actually controlling this size of the initial data, and that's why we put. And actually, if you see that lifespan of this equation was given by in terms of this size of the initial data. So that's the purpose actually, to control the size of this initial data.
Okay, and then later he asked, Tobias asked, additionally, does your critical exponent depend on epsilon or not? He asked.
No, critical exponent doesn't is for epsilon. It doesn't depend on epsilon. It's independent of epsilon. Indeed, it's only depend upon homogeneous dimension of the group and homogeneous degree of this Rockland operator. That's that's the thing. So you can see here our critical exponent is given by this, and it doesn't depend upon epsilon. So, but for the globe, this is the part. So here you can see that it depends upon this gamma, which is we take an initial data, but it doesn't depend upon size of the initial data. It just depends upon the order of initial this space of subglobe spaces. So these are the. So even I mentioned here, you can see.
Okay, thank you to Tobias for the question, and also to Vishvesh for answering Tobias' question. So, okay. Dr. Vishvesh Kumar, thank you very much for your presentation.
Thank you very much for inviting me indeed.
It was a pleasure to have you, of course, today. You are welcome always to our activities in ICMA Latin America.
I don't know how to stop this. Could you please do that, or is it possible?
Okay, thank you to all the participants that are following our conference. It's with great pleasure that I introduce the second speaker today, Professor Sabrina Roscani from the Universidad Austral, who will talk about on the two phases of one-dimensional fractional Stefan problem. So, Professor Sabrina Roscani, thank you very much for accepting our invitation, and please start the presentation.
No, first of all, thank you, Duvan, in behalf of the organization of the Isaac Ikman, because for us it's important to get the opportunity to participate in international conferences. You know, we are very far and we not so many funds, so this is a great opportunity. So thank you, and thank you all that are there in any parts of the world listening to the talk. So let me start. I will talk about the two phases fractional Stefan problem. The idea is to present a model and its weak formulation. Okay, so we will start obtaining the fractional Stefan problems from a fractional balance. We want to present such a physical formulation and not just changing a classical derivative by a fractional derivative. And then we will work with this problem in the aim to transform it and get another one related to the weak formulation that we think it could be very useful in literature for future work. So let me introduce you first regarding Stefan problem. When we talk about Stefan problem, we are thinking about a process where some thermal process is starting and we have some material which has the property of a change phase. For example, this is just an example. It can change this phase from liquid to solid. It could be from liquid to gas or even solid, anything. We are just, this is an example to figure and think about. During the talk, I will always refer from liquid and solid, just an idea to to think about in which region we are. So we have a domain that it's we will suppose that we work in the entire semi-X. So we will suppose that this is a cylinder with a very, very large length, and that the solid phase that is characterized when we have a free boundary. We want to know about the temperature in the two regions and the free boundary, which is our second unknown. Okay, so for every t, our domain is going to change. Okay, it's changing at everything. So what is the most important features from these kind of problems of phase change? The first one is the enthalpy. For us, the enthalpy will be the heat, the energy total that has part in the process, and also we will look at the flux, at the heat flux. As you can see here, the enthalpy is determined by the sensible heat. This is U will be our temperature. This is the one part of the heat energy, and this other rho L that we see here is a latent energy. The latent heat, which is the energy that will be used every time to change from one phase to another. Okay, so this is when we are not considering a phase change material, we only have this, the left part, but we have now this latent heat that will be the one who takes part in the transition of the solid one phase to another. Okay, we supposed here that we will have constant thermophysical parameters. So from the first law of thermodynamics, it says that the rate of heat in our volume equals the flux of heat across its boundary, okay? Or let me express it in this integral form. I know it is not usual to look it in this integral form, but it is just the difference, okay, of at any time of the energy with respect on the initial energy will be, we can measure it along all the heat that has flux across the boundary during this time. Okay, this is in this formulation in its integral form is just to introduce then the fractional model. Okay, so the classical formulation for a two-phase Stefan problem with classical derivatives is the following, which is define the functions, the enthalpy, the temperature, and the free boundary S, such that this function has some regularity. The enthalpy is linked through the temperature to the temperature through this enthalpy function that we looked before. Remember the sensible heat and the latent heat that was there, and the we have the balance equations for these problems are verified. The importance here is that this is a standard balance equation from the temperature, and here because we are considering a phase change material, we have the enthalpy. But the interesting thing in this kind of problems is the existence of a specific balance at the which comes from the can be derived from the path when we have at the moment that we have change in the phase, there is a jump which is caused by this latent heat that is taking part in the system, and we have a second. So we have a second balance equations. It can be also referred or derived from the Rankine-Hugonois equations that is Here in this approach in terms of the derivative of this fractional integral. Okay, so this is the fractional operators that will be considered in this talk and in this model. Just for the ones that who doesn't know this kind of operators, it is the fractional integral behaves like a semigroup. We can integrate or differentiate the powers. We know how to integrate or differentiate powers of a function, and especially the fractional Riemann-Liouville derivative of a constant, it is not zero. And this is just a particular characteristic. Here, I'm sorry about this one. We are not working with Caputo derivative. Also, we know that the Riemann-Liouville derivative is the inverse operator of the fractional integral derivative, as expected, as usual in usual calculus, but you just can imagine that if alpha equals 1, we recover the classical derivatives and the classical integral. And of course, if we do it in the converse form, it is not we do not recover the function. We just have to add some other terms as in the usual case. Okay, so another characteristic that working with these fractional derivatives is that we have it is not valid anymore the chain rules, and it is not valid also the Leibniz rule. But in this talk today, we will focus just in the model, and we will not have so many problems regarding these facts. In fact, I think that if I'm not wrong, the most important thing is that we will apply the Riemann-Liouville derivative sometimes as the inverse operator of the fractional integral, and that's all. Just if we focus in the model, of course. So let me return to the first law of thermodynamics, and when I said that from that law, it was I can understand that this the increase of the energy and at some time t equals the generalized, we can say, sum of all the fluxes in the flux fluxes acrossing the boundary during this time. Okay, so we will change this right hand side by, suppose now that we change the classical integral by a fractional integral of Riemann-Liouville. In a physical sense, it could be an interpretation to think about that the fluxes occurring at the beginning are less important and has less are less important than the ones occurring just at this moment. Okay, we are thinking that this, for the classical integral, all the fluxes has the same weight, and if we introduce this fractional model, the recent fluxes are more relevant than the past ones. Okay, so if we write this in this idea of giving relevance to the new fluxes in this energy or balance equation, we can write it in terms of fractional integral. Okay, so let us move now to a one-dimensional case, and the idea is how will be the equations of a fractional Stefan problem, so of a phase change problem, if we start with these balance equations. So we take an arbitrary volume, a little volume, And so these balance equations in this one dimension is given by the equation here. Okay, I have supposed that this is a cylinder with cross area constant, so maybe the area of this cross section could be should be in both sizes, and it has been cancelled. So let us work with this equality. We have the balance, this fractional balance, and the Fourier flux in the end to obtain the governing equations. So as usual, when we work with phase change problems, we will think about what happens when we move in the solid phase, when we are in the liquid, and then which will be the equations if the free boundary is part of our volume, this little volume that we have chosen. So suppose that we have these 2 points in the solid phase, then the enthalpy is characterized by this function. Remember that in the liquid phase, the latent heat is part, which is not here, is part of this energy, and that energy will be used to be part of this phase of change phases. So when we are in the solid phases, this latent energy is not part of the energy in this side of the systems. Okay, so the enthalpy, as I said before, is given by this equation just in terms of the temperature and the sensible heat here of the solid part. And if we apply this Riemann-Liouville derivative to both sides, you know, if you look here in the pink equation, we will have that it is the inverse from the right hand side, and in the left hand side it is quite easy to see that this operator in this case comes inside the integral. We have no problems. We assume all the regularity that can be assumed from this temperature. We have no jumps, anything, so it behaves very well. And using, this will be cancelled, and replacing this flux with the Fourier fluxes, and then using the first fundamental calculus theorem, we have that this equation holds in our pieces of bar or of volume. So in this way, being these x1 and x2 t arbitrary points, we get the fractional differential equation that is governing the solid phase. Okay, so if we move from the liquid phase, what is happening now? We proceed equals as before, and we get the classical this fractional differential equation for the liquid part. Just to know that we have added here a characteristic time, just to give a consistencies to the dimensions in this equation. If we want to analyze the dimension in these equations, we need to characterize or to add some characteristic time. You know that these procedures is usually done when non-Fourier flux are considering, like for example, when you in Cattanèo's equations, then a characteristic time is used to balance dimensions. Okay, so believe me that when we work with the liquid phase, we get the same equation. Of course, here we have the KL, which is the conductivity of the liquid phase, and in the previous one we have the Kas, which was related to the conductivity in the solid phase. Okay, so let us look what is happening now if we take a piece of volume, just that the free boundary is part of this volume. Okay, so we will assume that the free boundary is an increasing function. This is interesting because in the fractional case, we have to assume that the free boundary is an increasing function. And sometimes when we work with classical derivatives, under certain, of course, assumptions on the boundary conditions, we don't need to assume that this function is increasing, because we can use some Hopf lemma or something like that to make some conclusions regarding the behavior of the free boundary. But this is not the case for the fractional case. The maximum principles, the extreme principles are different from the classicals, but this is not our concern now. Indeed, let me assume that this function is increasing. Of course, this assumption is possible. In fact, if we work with constant condition at the boundary, we know some exact solutions or explicit solutions in terms of self-similarity ones. So this is this characteristic of assumption is possible. And so if it is an increasing function, we can identify its inverse function as this h, which for every x here, it will tell me the time such that the phase change is occurring. Okay, and this will allow me to differentiate from the solid and the liquid region when I am considering such time. Why? Because when working with classical derivatives, we are only concerned about the local flux, the local energy. But when we work with these fractional integrals of Riemann-Liouville, they have the memory is in the system. So if I am in some point here, I will be in this operator in my equations. Everything that happened before will be part of the system. So it will be important to me to look what happened here or to have a reference that about when did the change of phases hold. Okay. Also remember that the feature one of the classical Stefan problem was related to this jump in the free boundary of the flux of temperature in the free boundary that was related to the advance of the free boundary, and we will look what is the case here. So this is just mathematics. I start again as before. I apply the Riemann-Liouville derivative to both sides in these equations. And the fact is that now, remember that the Riemann-Liouville derivative is the classical derivative of a fractional integral, okay? So when you start working with this expression, imagine that I apply fractional derivative here, Riemann-Liouville. Okay, if the free boundary is taking part in this in this integral between x1 and x2, and we know that at this point the enthalpy will change. We will have one enthalpy in the liquid zone, and we will have another different enthalpy defined in this one. Okay, and also when we differentiate, we will have this parameter here, the free boundary. So we want to differentiate in time, and the parameter is in the integrals, and we have to apply classical calculus to compute this to pass the fractional derivative from the left side inside the integral. Right? Some limits will be appear in this case, of course, because the free boundary, which depends on times, is in the integral. Okay, so the point is that this limit, okay, is regarding the enthalpy that was in the limit is linked to the memory, okay, and it is when this part was a solid, and this other limit is linked to what is happening just in the free boundary, as well as the second one. Okay, so the point is that there are two limits that we can see here that will be cancelled, and the other one, which is this limit, which is related to the integral, the fractional integral. I'm sorry, there is the gamma is losing here, but is not important in this limit. So this is a fractional integral of an enthalpy function that we are assuming that it is, for example, a bounded function up to some time t. So this limit equals 0. So we don't have the jump now that we used to have in the classical case is removed now, and the classical Stefan condition that was regarding that we used to have in the classical case, here where now is a 0, we used to have the advance of the free boundary. Now it's not taking part, and we just and the conclusion, it is just the flux is continuous at the free boundary. We have lost the jump. So by using the fractional model, this fractional balance, we have lost the jump, the classical jump of the flux in the free boundary. Okay, so if the classical formulation for this problem, the fractional Stefan problem, under the assumptions that this the free is a sharp interface model, and the enthalpy and the temperatures, all the thermal coefficients are constant, is the following. It's just to find the functions u and h, the enthalpy, as we said before, with enough regularity. This must be adjusted every case. Just that the balance equation, we can write it in just one, just changing the subbing. How do I say this in English? Okay, so this little letter here from solid to liquid, and the classical Stefan condition is now just this jump of the free boundary, of the flux at the free boundary is not longer occurs. Okay, suppose that we add, as before, some initial and boundary conditions. So this is the problem. There is not a lot of literature about this kind of problem, especially related from the two phases. You will find in literature maybe some other kind of formulations where some memory fluxes or Caputo fluxes or the fractional interpretation is taking part more in the Führer flux or in changing the classical flux, but this one is obtained just considering a fractional balance. Okay, so if we, I would like to have a formulation which seems closer to the classical one. You know, when I want to have a better notation for this problem. So in the end, to do that, because I think that with a good notation, we will be able to deduce new properties, or it will be better to work with the problem. I will just write the fractional Riemann-Liouville derivative of the enthalpy as the classical derivative of the fractional integral. Okay, and I will I will name this fractional integral of the increment of the enthalpy as H alpha. So the classical formulation for this problem now is in this way, and as we can see, we just the fractional integral is inside this operator, this new definition, and it seems to be the original phase change Stefan problem for the classical derivatives. Okay, so let me make at least the this transformation, because I would like to change this one and think about some continuity of the flux of the temperature at the free boundary. Indeed, if we define this new function caplog u, which is known as the Kirchhoff's transform, then the problem, our fractional Stefan problem, now becomes the problem to find the temperature and of course the free boundary, such that our temperature is continuous, but the flux is also continuous in our region, and the balance equation still the same. We don't have K anymore, so we don't have to separate here. And note that the condition at the interface is now incorporated just in the regularity of the function. So we think that this is the most beautiful equations that we can have or obtain related to to start working with fractional Stefan problems. Just to tell you that this balance, the fractional balance from where we have started, it is a new statement that has been published and in collaboration with Professor Boller from the University of Minnesota, and it's this fractional balance is from 2023 and 24, from the past 2 years. So we are just starting this model, and there is a lot of things to do. For example, we have started to, we would like to start to, I wonder, what about a weak formulation related to this problem? Because from other kind of fractional Stefan problems, the weak formulation was not possible, but the formulations were different. I think that this one, which is very similar to the original, to the classical one, the weak formulation can be obtained. Okay, so recall that this derivative of H alpha is just the Riemann-Liouville derivative of the enthalpy. Sorry, there is a mistake because we have to subtract the initial enthalpy here. Okay, so what do we know about this problem? For example, the initial condition when we make this H alpha, the time go to 0. If this enthalpy behaves well, just it does not explode, this limit will be 0. So when we put H alpha in the model, we are losing in such a way the initial condition. So the initial condition that was part when at the end of the model, now we address the problem with the initial conditions, now is part of the operator. The initial condition is incorporated in the balance equation, in the governing equations. Okay, so a classical way to obtain weak formulation is just to multiply by a function and integrate, and then using classical arguments and standard arguments from calculus, we just developed the left part, the part regarding the fractional enthalpy, and then we looked at when we want to pass this derivative from the test function, some limits appears. But remember that this function is not the classical one. It's not the classical enthalpy because it is smooth, it is continuous, so this will cancel. And also we already take attention that this is the initial condition for the fractional enthalpy is given by 0. So it is very easy to become this derivative to change the derivative from the test function. Sorry, this should be a 0 here. Okay. So regarding the other part of the equation, the part of the temperature, we have already made the transformation. Now this step should be done if we were working with the classical Stefan problem, but I just wrote it here to say that it is not longer needed here because the flux, the derivative of u is now a continuous function, so these limits will agree, and it will not be take part anymore of the solution of this part integration. And then when we integrate again to have just the u alone, the conditions of the test functions at the extremes, we also can assume this is the boundary condition in the left side of the Robin type, and we can also suppose that at the extreme D, which is very, very far, we have some isolated point. Okay, so when we put all these equalities together, we have this new equality for the fractional for the fractional Stefan problem named to deduce the weak formulation. Okay, so what do we ask to this function phi? What can we ask to this test function? Okay, this is classical to ask this phi that at the last time equals 0. This is our classical, and these conditions phi x and phi x in L are we asked them to just to cancel some terms in the integration by parts at the extremes. This is as usual. So the weak formulation from this fractional Stefan problem will be the problem to find the enthalpy and the function u and the temperature u, such that this fractional enthalpy is we will ask some regularity to make these equations make sense, and that for every test function that is under this in this set of test functions, this fractional integral equality holds for every phi. Okay, remember that H alpha was the fractional integral of the difference of the current enthalpy and the initial one. So the initial condition is gained just in H alpha, in the H alpha operator. So we also, of course, we ask how to return to the classical, to the weak formulation, to if it is possible to return to the weak formulation to the classical one, and in fact it is, but we just need to be careful about the value of alpha. Okay, the idea to make sense to the initial condition when we work with fractional integrals I don't know if maybe there is some new theorems now, but the one I used was this one from 2018 from Professor Yamamoto and Kubica, which says that if we have a function in some Banach space and is with some initial condition, then this function is continuous in the sense that we can make this evaluation at the initial time for every alpha in 1/p1. So it depends on some LP space where the Wagner space where the function is. Okay, so in our case, we work with L2. So we will recover the classical solution if alpha is greater than 1.5. So, and this makes sense. This makes sense because alpha is between 0 and 1. When alpha equals 1, we are in the classical case, but when alpha equals or is less than 1.5, we are from the other side. We are almost not close to a classical diffusion equation. So and we may lost some regularity, and okay, it makes sense that if we are in the diffusion part of the problem, then we will recover the solution, the classical solution, and if we are not so close to the diffusion problem, some things happen. Okay, so as I told you before, this formulation is new, so this balance. Fractional balance is new, so we are. This is just the starting work in our in my current research in this line. So I really would like to continue studying existence, regularity. I have an idea to prove existence of this problem, but I did not finish yet. And of course, this enthalpy, this enthalpy or fractional enthalpy that is involved here makes sense to work with numerical simulations. And Professor Boller is an expert in such areas, so we are also working on that. Okay, so I'm done. Thank you for your attention.
Okay, thank you very much, Professor Sabrina Roscani, for your very nice presentation. So it's time of questions. Does anyone has questions for Professor Sabrina Roscani? Remember that you can make questions raising your hand. Okay. Okay, maybe I can start making some question about your fractional balance equation, right? Mm-hmm. Which was a central point in your discussion, right?
Yes.
Here, right, exactly here. Okay, so my question is if you know, in mathematics sometimes one likes to make generalizations. If it doesn't make sense, for instance, to put somehow time-dependent coefficients, let's say in the right-hand side of your equation. Maybe it was not clear, maybe in this equation, but in another one where you wrote like partial derivative of t, h with the power alpha, minus second derivatives with respect to h of u equal to 0. I think that was in another slide.
Okay.
I think
maybe in the next one.
Maybe later, right?
Why are you thinking on time-dependent coefficients?
No, just see if maybe it's possible to adapt your equation to that setting. Just thinking that, for instance, when one has heat or wave equations, usually one also put coefficients to the main operator, let's say the Laplace operator, and one put some coefficients. And then if one make analysis, let's say via Fourier analysis, then one can also adapt the analysis to those settings. It is indeed in that way that I am thinking maybe that one can put time-dependent coefficients, but it's not.
No, I understand. In my experience, I think it could be dangerous because we don't have this Leibniz rule when differentiate or so it may difficult the to work with this if we add this time dependence, for example, to the liquid conductivity here. But it may be possible. Maybe we could. It would be better if we make, and it has also sense that the conductivity maybe is more related to the position and not just to the time. So if we add some spatial dependence, it will be fine because we are differentiating it just in time, in the fractional sense. So maybe that is a good possibility. I think that the group here in Rosario has studied this some special classical Stefan problems with this dependence, some dependence of the parameters on the position, and they have found self-similar solutions. But where in terms of some special functions, I don't know, maybe Kumar, but I was just associated with the former professor, but maybe I'm wrong. I don't know. This is the same special function of his surname. Okay, so.
Okay, I see. Thank you. That was maybe an abstract question, but I see you are mainly motivated by your physical problem, right? That was to consider this bar with the liquid part and the solid part. Maybe another question is if one can has a closed model when you have, let's say, the liquid part, the solid part, and maybe one measure between solid and liquid part, right?
Yes.
You know something about it?
Yes. That kind of models, usually you have liquid, some interface, some region where you don't know what is happening, and then the solid one. These models are known as Mashi zone models. So, but the Mashi assumption must be done at the beginning of the formulation. As I said in this talk, I was very nervous at the beginning, and I did not say, "Oh, I am obtaining a sharp interface. I'm starting from a sharp interface assumption." If you don't, you may assume this zone, this Mashi zone exists where you don't know exactly what is happening, and different models can be obtained. Usually, this model is obtained from defining a different, instead of defining such enthalpy like this, like we see here, they put a function of the latent heat that is verifying some properties, and in terms of that function, you work with a Mashi enthalpy model.
Okay.
It calls a liquid fraction. You add a function which is not linear, not nothing. You don't know very much, but it is a liquid fraction, and you just you measure how much portion of liquid is in every time.
Okay. Very interesting. Okay, I think maybe there are not questions for Sabrina. Just maybe then let me say thanks to Professor Sabrina Roscani for her presentation. It was very nice to see several presentations from researchers from the Universidad Austral in Rosario. So it was nice to see a perspective of the mathematical research that they are doing there. So we were very happy to have all of them.
Thank you.
during
Thank
this
you
week.
for give this space for Austral University in such an international conference.
Thank you very much to all of you for your interest in participating.
Okay.
So, thank you. So now I think we have somehow 10 minutes before the start the next talk by the General Sinman from India. But then I think maybe we can have a short break of 10 minutes. Then see you in 10 minutes.
Duval.
Okay. So it's my great pleasure then to introduce our next speaker, Dr. Jitendra Singh Man from India, from the National Institute of Technology in Hamirpur, India, who will talk about wavelet transform associated with the index Whittaker transform. So first of all, thank you very much for accepting our invitation, and please start with your presentation. Thank you.
Thank you so much, Professor Duan and entire team for organizing such a great conference and giving us the opportunity to present my work. So the title of today's presentation is Wavelet Transforms Associated with the index Whittaker transform. So in this presentation, I will discuss how we have defined continuous and discrete version of index wavelet transform associated with the index Whittaker transform. And with using the convolution theory of this index Whittaker transform, we have developed wavelet transform and obtained its Plancherel relation reconstruction formula and norm inequalities. Further, using the discrete wavelet transformation, we have obtained the similar properties as that of the continuous wavelet transform. So these are the outline of today's presentation. Now, what is wavelet? A wavelet is a wave-like oscillation with an amplitude that begins at 0, increases, and then decreases back to zeros. The concept of wavelet or ondulet started to appear around 1980s. So this concept can be seen as a synthesis of various thoughts and ideas originating from the different disciplines of mathematics. The idea of wavelet transform was first discovered by the French geophysical engineer, which is Jean Morlet, around 1982, for providing a new mathematical tool for the seismic wave analysis. The idea of wavelet transform that came into existence to achieve good time resolution for high frequency transient and good frequency resolution and wavelet transform in various fields of science and engineering, like in image processing, biomedical engineering, signal processing, computer vision, etc. Now we will see what mathematically a wavelet means. A wavelet are a family of functions which are created from translation and dilation of a single function. This C is the dilation and B is the translation, and where B and C both are real and C is non-zero, of course. Here the C is called the scaling parameter, which measures the degree of compression or scale, and B a translation parameter, which determines the time localization of this wavelet, and for which is given by translation and dilation, that is by this integral, where we define the dilation by this dc phi of z given by this, and this dz dx in terms of Dirac delta function, which is given by this. And so if the scale and positions are varied smoothly, then the transform of this is called a continuous wavelet transform. The continuous wavelet transform of any signal, say f in L2R, with respect to wavelet in L2 is defined integral, and you can see that any continuous wavelet transform can be expressed in terms of a convolution operator. So therefore, wavelet is a special kind of convolution operator, and associated wavelet is known as the classical wavelet or the mother wavelet. Now you can see since translation and dilation as well as kind of operators and the above notions, many authors have constructed wavelet and wavelet transforms in terms of fractional Fourier transform and studied their properties. So in addition, some more wavelet transforms have been developed, established to half-line using the transform of transform, wavelet transform, contribution with Lebesgue wavelet transform, and discuss their properties and applications. So in this presentation, we will discuss the wavelet transform associated with the index Whittaker transform, which is also a famous transform defined on a positive half-line. The index Whittaker transform is Whittaker convolution. Many fundamental results for these transforms are already known, but study of wavelet and wavelet transform involving index Whittaker transform is still missing. So motivated by the previous work, our aim is to define wavelet and wavelet transform in the index Whittaker transform, and further their theory and basic properties in this correspondence. So we will consider a Lebesgue space LPR plus defined on a positive half-line, which is proposed in reference number 26 as the space of all those real value measurable functions which are defined on a positive half-line, such that the following norm is mx, which appear to be a weight function in this integral, is given by this equation, and it is clearly stated that for P restricting between 1 to infinity, including 1 and infinity, this space is a Banach space. Now, in the references, you can see that index-Whittaker function, a solution of certain differential equation of order 2 by various authors. So, which are Srivastava, Al-Musmallam, Sosa et al., etc. And Becker has extended the theory using the Whittaker function as the kernel in mathematical physics. So, in this sequel, we will consider the definition of index-Whittaker transform, which in his paper in Journal of Mathematical Analysis and Application, we are using that definition of index-Whittaker transform, which is given in terms of the integral 1. So, this function psi, which appears to be the kernel of this transform, which is a Tricomi function, and its relation with the Whittaker function is given by this. And by a certain table, you can relate this Whittaker function in terms of confluent hypergeometric function. So simply, our kernel is actually a special kind of a confluent hypergeometric choice of index. This transform can be reduced to the Counterwich-Lebesgue transform, which has a wide range of applications. Now, where 1f1 appears to be a confluent hypergeometric function of first kind, and this to be a Whittaker function, which is studied in these references, and this side is the Tricomi functions. Now, again, we will recall the integral representation of this kernel in terms of some spatial functions. Our kernel can be expressed in the integral representation, which involves this Legendre function, and we have obtained another integral representation of the kernel, which is given by this integral. We have the bounds of the kernel, which are given by this reference. We have this bound given by this equation number 2, and the asymptotic behavior of the kernel near the singular points of the transformation are given by this. And to study any transformation, one should know the inversion of this index-Whittaker transform 1 in this Lebesgue space is given by the equation number 3, where this major rho a tau appears in the integral 3 is defined in terms of this. Now, our interest is to find the adjoint of the index-Whittaker transform. So, it's equation number 4, just as the measure comes outside, and the inversion of this 4, again, the adjoint inversion is given by this equation. Now we will study the convolution structure of this index-Whittaker transform. As we know that the theory expanded from Fourier to then wavelet transform. Since Fourier, the outcomes in Fourier transform are localized in the frequency domain, whereas transform one work using the window function, and but to come drawbacks of certain signals, one move to wavelet transformation. So with this hypergeometric kernel functions, our target is to achieve wavelet transform. To move to the convolution structure of our transformation, the product formula for the confluent hypergeometric functions of the second kind with different argument can be given by equation number 5. You can see this is the product of kernel with different arguments in x and y of our transformation, and it is related by. Now you can see this function qxyz, which appears inside the integral, is given by this equation, where this d mu z is a parabolic cylinder function, which is a solution of certain differential equation of order 2. Here you can notice that this qaxyj is symmetric in all the so this now you can use this equation number 5 and remember the definition of index-Whittaker transform. You can see that this is the kernel, this is the function, and this is the measure. You can see this is simply the right hand side of equation number 5 is index of this function qxyz, which can be expressed in terms of product of the kernels. So I can use the definition of IW transformation and equation number 5. So this is clearly the definition. This is the index Whittaker transform of this function, which is expressed in the product. Now to get the integral representation of this Qxyj, so I will apply inverse transformation. So inverse IW transformation of this will be the integral with respect to major rho. So we have this representation of Qxyj, and another representation we have obtained in terms of the by applying the inversion formula. Okay. Yes. Now, as I already told that this Qxyj is positive for all non-negative and since these variables are positive, since our domain is R plus, and that is positive half-line, and we see that it is symmetric. Integral of this Qxyj with any measure with respect to any variable is 1. So we will use this while computing and establishing the result associated with the wavelet transform, continuous and discrete version. Now it is important to know the translation. So the translation associated of integral. Remember that while studying Fourier transform, we use the translation just as translation with respect to say variable c is f of x minus c, but here translation is integral. If the translation is integral, so it is well known that the convolution must be an integral operator again. So the adjoint of this integral, right? And further, using the translation operator, we will define the convolution of two functions. So convolution is defined in terms of this integral translation of this function f and this gz with respect to measure mj dz. Remember, the integral representation of the convolution can be expressed in terms of the double integral. So one more thing, so we will use these properties frequently in our upcoming results. So the index Whittaker transform of a translation and convolution satisfies the following result. Transformation over the translation of a function, you will get the kernel times the IW transformation of this function. And this is the important property that if you apply IW transformation over the convolution of two functions, you will get the IW transform of the corresponding functions with their product. So this is also true in case of Fourier and many other integral transforms. So we have the another lemma that if f is a member of L2 and g is a member of L1, then this norm convolution is controlled by the product of these two norms in L2 and L1 respectively. So this is reference number 13, and one can get the. Now another thing to study any kind of integral transform is to get the Plancherel and Parseval relations. So you can have the Plancherel relations given by this equation number 14. If f equal to g, this will turn into equation number 15, and you can see that it is an space with measure max and this rho eta, which is defined for the inverse transformation. And we have also established the Plancherel and Parseval relation for the adjoint of index Whittaker transform, which is given by 16. And if you put f equal to g, it will turn to this integral. Now, since all the study related to translation, convolution, and many other properties are well known for the index Whittaker transform, so we will define our continuous wavelet transform for the Whittaker transform. A function phi in L2 is called a Whittaker wavelet if it satisfies the following divisibility condition. So we can remove modulus since the integration is from 0 to infinite. This should be finite. And for any function in LP, we will define the translation for this corresponding Whittaker wavelet to be as product with this variable, and C is of course. Now, that is dilation. So mathematically, a wavelet is nothing but a translation and dilation of this function. So we will define with this wavelet the is defined as by using translation. Remember the definition of translation and dilation, as I had told in the previous slide. For any wavelet, Whittaker wavelet phi, which is a member of L2, the family of Whittaker wavelet can be expressed in terms of this function phi Vc of x. We need to translate and dilate this function. So this is dilation and operated over time translation. We know that dilation is nothing but dc phi of z. And remember the definition of translation, integral 0 to infinity. This is our function qx dj mz dj. Now this dilation in the previous slide I told, so this is actually the integral representation of our wavelet. Now where B and C both are positive, now the function in L2 with respect to Whittaker wavelet, which is given for a function phi which is in L2, is defined in terms of inner product, that is integral 0 to infinity signal. This is the conjugate of this Whittaker wavelet with respect to measure mx dx. And again, you know, so this can be expressed as the double integral, which is given by 20. So this is our actually continuous wavelet transform associated with the Whittaker transform. Now here comes the some existence theorem which states about the continuous Whittaker wavelet transforms as a member of LP, and phi is a member of LQ, where P and Q are related by this relation and both are conjugate. And this continuous Whittaker wavelet transform be given as discussed in the previous. Then for the arbitrary fixed constant C, these following results hold. We state that the transform, continuous Whittaker wavelet transform, is a continuous with respect to variable B on this domain. And next result is this norm inequality hold, that is the norm of this LR norm of this continuous Whittaker wavelet transform is controlled by the product of these two norms, which is F in LP and this is in LQ, and this PQ are related by this. And next result is L infinity norm of this continuous wavelet transform is controlled by the product of these two norms. This is actually a consequence, this result is consequence of B if you put R equal to infinity. So there is nothing special with this case. Now we will discuss that how this continuous wavelet transform is with respect to wavelet with respect to variable B on this domain. Now we consider an arbitrary point B naught C, but fixed in this domain. Then we will apply the Holder inequality to the following. So here, so we will apply Holder inequality. Remember the definition of this continuous wavelet transform. So this will be in terms Holder inequality less than or equal to this, and using the value of this integral representation of qxyz, as I have already told, the integral of xyz with respect to mx dx is 1. So this the continuity result follows. Now, yes, this result proof of B and C is obvious and it can be found in this reference. Now here are some properties associated with the continuous Whittaker wavelet transform. Suppose phi 1 and then the continuous Whittaker wavelet transform satisfies the following property. The very first is linearity. So linearity will follow. Anti-linearity, you can see this anti-linearity property. Now the next result is, suppose if phi belongs to L2, then the index Whittaker transform is given in terms of this relation 21. So if you apply IW transformation over this mother wavelet, you will get kernel times this IW transform of this function, and this function is nothing but the integral of this, right? So I will simply Whittaker wavelet and apply the Whittaker transform on this. So this will be the kernel times this integral representation of the mother wavelet, which is given by this, and mj dj. Now you can take this outside, and this is actually our this can be expressed as the product of this previous slide. This can be expressed, we remember, can be expressed as the product of the kernels with two different arguments, the same result I am applying. So I can express it in terms of these two different arguments. And using one of these MSI I can rewrite this nothing but the IW transformation of this function. And this is nothing but the integral of this phi of z with respect to measure yes, B. Right. Now, next is lemma. If f is a member of L2, the any function and phi is a member of L2, which is a Whittaker wavelet, then we have the following result that number 22. You shift this operator to this, you will get equation number 23. And this equation number 2 will be used in the next slide to obtain the Planck-Searle formula and the reconstruction of the function f from the continuous wavelet transformation. So here, remember the definition of this previous result. We have established that this can be expressed as the kernel. And remember one thing, that this should be a conjugate of this kernel. So it is a real quantity, so it will remain as it is, and it will automatically follows that this is a inversion, inverse IW transformation of these two functions. So this is inverse, and apply IW transformation on both, you will get the result. This is 22 of the previous slide, and this is 23. So next is the another representation of the continuous Whittaker wavelet transformation. As I have already told you that this wavelet is a special convolution operator. So in our case, the wavelet transform which is defined for the index Whittaker transform is also a convolution operator. So this is the definition of our continuous Whittaker wavelet transformation. So this is actually nothing but the translation. So this is translation of this function, and this is another function, and this is the convolution of these two functions. Now we will see one example. So let us suppose that fx be given by x to the power beta, where a is less than beta and non-negative a. Then using this previous lemma, the continuous Whittaker wavelet transform of this fx is given by. So this is the definition of our continuous Whittaker wavelet transform. So in this lemma, that is this well-known integral will reduces into this Tricomi function, which is 24. Now I will choose this wavelet phi as a B-spline mother wavelet of order 1, which is given by bija equal to 1 within this 0 to 1, and it is 0 otherwise. So our function, which will have this to be 1 on this domain, and it is to 0 to be otherwise. So substituting this 25 and 24, so you will obtain the continuous Whittaker transform of the given function x to the power beta, which is given by this integral. Now, the next of important result is to obtain the reconstruction wavelet transform. We will obtain, suppose that if f is in L2, and this sigma of c be a positive weight function such that this following condition holds. If you look at this condition, the sigma of c, choose sigma of c suitable condition holds, and phi b x function which expressed by 27, then our function f can be restored by this double integral. So proof is to use relation number 23 that I have already told, 22 and 23. So remember that integral of this continuous wavelet transformation is expressed as this product of these two IW transformation. Now if you apply, means multiply both sides by this quantity sigma c and phi a, this is simply nothing but we are trying to make use of this integral 26. So this side will changes to c phi that I have already expressed in this. And now we will use in the next step relation 27, and then we will establish our result. So now this c phi transfer to this, since it is non positive, and this right hand side will be our IW transformation, which is expressed as this double integral. So yes. Next is now to apply Fubini theorem. You will apply Fubini to this and making use of the IW transformation of this function, which is expressed in relation number 27. So apply inverse of this IW transformation on this side. So this will get turns out to be function f, which is restored by the integral, which is given by this. Right. Okay. So now next is the characterization of this function, which is given by the relation number 27. Now assume that there are certain positive constant a and b such that c lies between a and b, both are positive and finite, which is given by 28. And we take some other function which is given by the relation 29. Then we have the following inequality, that is, this function can be expressed as the translation of this control by the a certain a inverse times the wavelet, which is a function of L2, right? So invoking the previous outcomes, we will use the definition of this, which is given by relation number 27. So it is actually IW transformation of this function. This transformation, so it will turns out to be this integral, and using relation 29 means this previous, you will get the first result holds true. For the second result, you can use the relation 27 and 28. That is, so you will get this relation and take L2 now. The next is that if phi is a member of L2, which is a Whittaker wavelet, then translation of this wavelet mother wavelet is a member of L2. That is, it is also a Whittaker wavelet. Now, by using this proposition, if f phi is a member of L2, then the translation of that function is also a member of L2. So clearly, the very first thing to claim that this to be a Whittaker wavelet is satisfied. This function is a member of L2. Now to check that this function is a Whittaker wavelet, that this should satisfy the admissibility condition. So we know that the IW transformation of translation of any function is nothing but the kernel IW transform of that function. So I took this admissibility condition, that is the IW transformation of this function square over tau d tau, and we know that this is nothing but the square of this quantity, and this is psi IW transformation of this function, and we know that this dominated by controlled by a finite means it is finite. So this is already finite. So this admissibility condition holds, and the theorems follow. Now next theorem is, if phi is in L2, then is again a wavelet. So the very first lemma I have discussed, that if this is a wavelet, so this must be a function in L2. This is a function in L1. Convolution will be a member of L2. So this is a member of L2. The very first thing is satisfied, and next is to check it is a wavelet. This integral should be finite, and we know that if IW transformation over the convolution of two functions, it will be a product of IW transformation of these two functions. And since this phi is a wavelet and H is bounded integral function, this is finite, and this is satisfy admissibility condition. So this integral is finite, and hence the follows. So this convolution is a. Now next theorem is Plancherel relation. Consider the two wavelets phi1 and phi2, which is a member of L2, be a Whittaker wavelet such that their IW transformation is related by this, and sigma of c be a weight function. I'm here specific with the weight, so that this integral is finite and no longer depends on tau. Then we have the double as this p phi1 phi2 and this inner product. So since f and g are in L2, so I will consider the right hand side. So this is integral, the continuous wavelet transformation of this function with phi wavelet transformation, and I am applying the Plancherel relation. So we know that by relation 22, this quantity means this continuous Whittaker wavelet transformation of a function with phi1 can be expressed in terms of inverse of this. Same thing is true with this term, and taking conjugate, and we'll remember that our inverse transformation over this term, and similarly to this term. So we will have this some bigger expression. So this quantity is real, And by using relation 16, that is Plancherel relation, you can see that this IW transformation will turns out to be actually and again this row A tau will get cancelled out, and this turns out to be this integral. And again, by using the Plancherel relation, you will get this integral, and using the relation 32, this can be expressed in terms of the inner product. Now, these are the some following consequences. If I want, if f and g both are equal, then we have this integral representation. This will be in L2. And if both are equal, f and g are equal, and phi1 and phi2 are equal, then we will have this double integral. Now, since we have obtained Plancherel relation, we have restored restoration formula. Now, next is we have the so composition of Whittaker-Wavelet transform using the Fourier transform theory is well discussed by Pathak. So motivated by the work of this Pathak, Prasad et al. Extended it to in terms of fractional Fourier transformation. So in this section, we will construct the composition of Whittaker-Wavelet transformation and discuss some of its properties. So consider these two continuous wavelet transformation with argument P and Q and RS. So all are in on positive half length. Then we will define the composition to be the integral 32 of this function f, which is the composition of these two continuous Whittaker-Wavelet transformation. So similarly, now 23. So you will obtain it in terms of this integral 33. So admissibility condition in this case, let us assume that phi1 and phi2 will be the Whittaker wavelet such that these following hold, and assume that I am specific with the zeta 1 to be 0x to be this, then this should be finite and no longer depends on tau. So the same relation we will apply for this composition of Whittaker-Wavelet transformation. So suppose phi1 and phi2 is a member of L2, which is a Whittaker wavelet, which defines the composition of these two, which is given by these two, and Fg this triple integral will coincide with this P phi1 phi2 times the inner product of Mx, where this is well defined in the previous slide. So consider the left hand side of this integral and the same computation as we have obtained the Plancherel relation. So if this leads to be this, and this is nothing but our right hand side. So if f equal to g, so this is the consequence of our Plancherel relation in case of composition of continuous Whittaker-Wavelet transformation. Now, since continuous Whittaker-Wavelet transform is different, so Wavelet transform has a large number of applications in mathematics, engineering, and computer science. Most notably, it is used for signal coding to represent discrete signal in a most redundant form, often as a preconditioning tool for data compression. So it has wide range of applications, basically in signal processing, image processing, biomedical signal processing. So in signal processing, the data are represented by a finite number of values. So discrete version of continuous wavelet transform to found to be useful, and more precisely, it can be achieved by choosing discrete values to translation and dilation parameter. So the same thing we will do, we will obtain the admissibility condition in discrete wavelet transformation. So with the help of continuous wavelet transform, by providing some discrete values to translation and dilation parameter, we will obtain our discrete wavelet transform associated with the index Whittaker transform. So for any function phi in L2 is called a dyadic wavelet if it satisfies the following condition, that is 37, where j is integer and a and b both are positive constant which are related by this relation. So in the condition 37, that is this, it is called stability condition. Now using relation number 19, that is our continuous wavelet transform. This is relation 19. We define semi-discrete wavelet transform for any function phi. Just replace the parameter c by 2 to the power minus j and b. Let the b to be a continuous in this R plus. So this, remember the definition of this continuous wavelet transform. Now we are replacing C by the factor 2 to the power minus j. So it will be in terms of this inner product. Double integral, that is the semi-discrete wavelet transform, and again we can express it in terms of convolution. So if you consider this integral fx with qx y measure, so yes, so it will be a translation, and this is the other function, so it is a convolution, and this variable b that appears here. So using the part transformation, this important theorem, assume that that the semi-discrete wavelet transform of any function in L2, which is defined in the previous slide by relation 38, and let us consider another wavelet phi satisfying 37 by means of a Whittaker wavelet transform, which is given by this relation. So we consider the right hand side of the above integral, and again we will apply the inverse, that is, yes, I will apply the inverse IW transformation. So we will have this. So you can see it can be expressed as the in this integral. So this is I inverse IW transformation with since rho a tau. So yes, okay. This can be expressed as the this, and yes, this function. Now you can write this in terms of convolution structure, and remember the definition of this psi f phi 2 to the power minus g, which is given by relation number 40. So by simple calculation this will cancel out, and what remains is nothing but our function f. This is inverse IW transformation of this function. So by using above theorem, it gives some motivation that reconstruction of f is possible under certain circumstances, which leads to the definition of dyadic dual of a dyadic wavelet. So the function f in L2 is called a dyadic dual of a dyadic wavelet phi if f belongs to L2, can be restored or can be expressed by this integral, and using relation 37 and 40, so we can similarly obtain the stability condition for the dyadic dual of a wavelet, which is given by this, right? Now, here is important theorem. Yes, if dyadic wavelet phi satisfies this stability condition, which is given in yes. So, then this wavelet phi satisfies this relation. If A equal to B, then we have the admissibility condition to be A times ln of 2. So divide 37 by tau and integrate with respect to tau within the limit 0 to 2. You will get this to be the integral. Now this integral in another, substitute 2 to the power minus j as eta. So by mere computation, you will get 42, and this value to be the ln2. So as the second part holds true. So in view of relation 38, we have discretized only dilation parameter to get semi-discrete. Now we are also restricting the translation parameter on a discrete set of points. Now we are interested in getting the discrete wavelet transform. So djk can be expressed as some fixed, and this where the factor Cj, that is 2 to the power minus j. We have only discretized the translation parameter. The other parameter is simply 2 to the power minus j. Just remember the definition of same will go for the discrete version, that is this continuous wavelet transformation. Now we have discretized the translation. This parameter, this scaling parameter was already a function 2 to the power minus j. It is expressed in terms of this inner product, and again by this definition we comes to the stability condition following for the discrete wavelet transform. Now we will do the reconstruction formula for this function f by means of the discrete wavelet transformation. So here is the result. So suppose Let discrete wavelet transform of any function phi in L2 defined by 38, that is the and P be a linear operator which is defined over L2, which is expressed by 45, then this F can be restored by this, and this function phi jk, which is discrete, appears to be the inverse of this discrete wavelet transformation, right? So we can see the proof from relation 44 and its P inverse exists and bounded. Let us suppose G to be a function of TF and F in L2. So by the relation 45, the relation, okay, relation 45 is this. So I will say, and from relation 44 again, we will have, since this is the inverse G equal to TF, so it will be the inverse of this, and using the relation 44, you will get this following inner product. And the next is to apply Schwarz inequality. Since f for every f in L2, this function can be restored from the discrete wavelet transformation, which is given by this summation, and this phi jk appears to be the inverse of this. Now, next thing is we have included in our presentation frame and race basis, which is in L2 for this discrete version of wavelet. So the theory of frames and bases have been developed rapidly in recent years and used as a mathematical tool in signal and image processing. So in this self-contained work, we have presented frames their mathematical properties. A race basis is an orthogonal basis under an invertible continuous linear mapping. So perturbing a race basis by a small amount yield another race basis, and frame many of the properties basis, but lack a very important one, that is uniqueness. Section we will basically discuss formation and study the race basis in L2. So remember the definition of function phi in L2 is said to generate a frame with this discrete wavelet of L2 with the sampling rate V0, which is given by equation number 44 holds for some positive constant A and B if right. So race basis. Now for race basis we have the two conditions that function phi f in L2 is said to generate a race basis with this discrete wavelet transform with sampling rate V0 if the following assertions are satisfied. The linear span of this discrete wavelet should be dense in L2, and there exists. So that is 46 to the holds to, and this djk which appears is a sequence in L2, and A and B are referred to be as the race bound. Now this is the last theorem. If phi is in L2, then the following statements are equivalent. This is in L2, and second is this discrete wavelet is a frame in L2, and also L2Z. This is Li family in the sense that this summation equal to 0. It means that this is a member of L2 and each of them is 0. That is, this should be Li. Moreover, the race bounds as well as on the proof which is proposed by Chui. So you can see that we will simply use the definition of race basis and the scheme of the proof which was proposed by Chui. So this is the proof. So thank you so much.
Okay, Jitendra Singh, thank you very much for your talk. Very clear talk. Just okay, at this moment, then we have maybe time to make a couple of questions to
Yes.
Jitendra Singh. So Does anyone in the audience wants to make a question? Okay, so Jair, please. Maybe you can unmute yourself.
Okay, now you
Yes,
hear me?
yes, I can hear you. Yes.
So thank you very much for the talk. Very interesting. From some physics.
Yes.
Not just like that. I mean that people want to like that to be interested in the integral with this specific kernel, which is the Trichomy function. Maybe, if I remember, maybe I have already seen this kind of kernel, and maybe it is connected to some Hamiltonian operator.
Okay.
Maybe it's some kind of relativistic quantum mechanics or something like that.
Okay.
But I already have seen some kind of this index transform, but they are coming from coherent states, which are tight frames, coming from this kind of this wave coherent state, which are the more general setting for wavelets theory. And there it's very interesting to see what is this. This is a kind of Bargmann transform for this kind of Hamiltonian model. There is a Hamiltonian model with a maybe specific potential function in a way that when you perform this coherent state, the coherent state transform associated with this model is maybe this Whittaker or Whittaker transform. And one of the questions also is to characterize the range of the L2 space. You have an idea about what is the range of L2, of the L2 space you start with. This transform is going from a Hilbert space, which is quite simple, like L2R plus or something like that. I mean, where there is this physical quantum mechanic motion, and then the image should be in some kind of analytic space, which is some space on the face, some doubling the dimension. I mean, the phase space.
Actually, the domain is already defined for this transformation, that is in L2 with measure in max dx, and measure function is already defined in the presentation in the start.
But what is the image, the range of this transform?
Sorry.
The image of this L2 space by this transform.
Sorry.
Maybe he asked about the codomain, right? You define your wavelength transform in some L2 space, weighted L2 space, and then Professor Zohair is asking to which space, right? The image of this transformation goes, right?
Yes, yes.
If it's another L2, maybe another L2 space.
Yes,
maybe?
L2.
Yeah, in fact, there will be some subspace, some subspace of some L2, but L2 on what? On something which is a double dimension of R, which is the phase space.
Okay.
And maybe the analytic side, like the Bargmann transform from L2R to the Bargmann space of analytic Gaussian square integrable function. We are here in L2 of C, subspace in L2 of C of analytic function. This space is very important because it may be also it may have some differential operator characterization. What we hope is that the kernel of the transform could be connected to one-dimensional Schrödinger operator, and the arrival space of the wavelet transform may be characterized by another Hamiltonian, which is in the double dimension space.
Okay.
And this is very interesting things. Maybe we may continue our discussion.
Yes, sure.
I may send you this physics of this kernel, maybe, and then we can continue talking about this. Very
It will be
interesting.
helpful for me to explore more abstract things about the wavelet transformation.
Yes, maybe like your equation. 35. 35 is like what we call square integrability of the representation, and then this is the resolution of the identity for the coherent states under consideration.
Okay.
So everything are connected in some sense.
Okay. If there are some result that can improve my more result, that I will be happy if you could share with it.
Yes.
That's sure.
Okay.
I mean, my idea is that a lot of integral transforms, the kernel of a lot of integral.
No problem. If I stuck in some calculation, we can discuss on it.
Yes.
Sure.
Okay, it's very nice to see then that our conference also serves as to establishing collaboration between different researchers, right? Like India and Morocco, which is very nice, of course.
Why not? Yes.
Okay, I think Bishbesh also has a question, right?
Yes, can I ask?
Please.
Yes, sir.
So, when you define this translation operator, Whittaker translation operator, what is the motivation like you define in this way?
So it is not defined by me. It is defined by Yakubich and his PhD student.
Yeah,
so I'm utilizing that result. So maybe the convolution structure.
What convolution structure is defined by translation?
Defined by translation, yes.
But why you define this way? That's my question, actually.
The function QXYZ, that is important. I think that appears in the definition of translation. So since involvement of that parabolic cylinder function.
In your you answered your slides, I think, right? Because I was thinking. I was having some question from your slide, but
yes, sure, I will share.
But I just
I think that it is also connected to the hypergroup story.
Okay, so
hypergroup stories with this translation.
So can you go to this where you have put this kind of inequality using Holder inequality, right? That lemma, I think there. Yeah, here, like previous slide.
Okay.
Yeah, here. So you see here, you put this condition on the top that 1 plus p plus 1 plus q is equal to 1, and then
sorry, I have to remove this condition since we are
in condition B. You are putting this.
Yes. I got it. Okay.
So it's so just a Young inequality. Actually, you don't need to put this.
Yes.
I think.
Okay.
Okay. Okay, it's just yeah, thank you. Yes.
Okay, thank you so much.
This remember me this question of translation operator and convolution structure with this story of hypergroups.
Okay, sure.
So I this was following a lot of works in Tunisia.
Actually, my study is basically on Rn. That is what we do with the Fourier transformation. So to extend this hyper, so I have to first analyze few papers, and if I find any of the difficulties while studying or having stuck in some work, I need your help, right?
Well, welcome.
Okay.
Okay.
Okay. Thank you.
Thank you so much.
Thank you to Sohair and to Vishwesh for the feedback, to Jitendra Singh.
Okay.
So Jitendra Singh, thank you very much for accepting our
Thank you so much
invitation.
for your valuable feedback and for your patience also. Thank you so much.
Thank you very much. Okay, maybe we have 3 minutes of break before our next talk. Yes, maybe Sohair, maybe you can start.
Yes,
sharing the
yes.
screen. Julián, I will make a presentation about you. So it's my great pleasure then to introduce Professor Sohair Mouan from the Sultan Moulias Limnain University in Morocco. Professor Sohair Mouan will talk about magnetic Laplacian operators on CN with reproducing kernels for their L2 eigenspaces. So thank you very much, Professor Sohair Mouan, for accepting our invitation, and please continue.
Okay, but it's a great pleasure and honor and I'm very happy to join you in this nice conference, and thanks to all colleagues from the National University of Colombia for this nice initiative to connect all these people. So I will talk about some operators and their the role of their reproducing kernels. So I have a lot of things. I will talk about the ingredients, which are spherical harmonics, then magnetic Laplacian on C in the definition, and the generalization of Bargman spaces on Cn, and their reproducing kernel, how they are attached to Landau levels on Cn, height and wave equations, and spectral decomposition of magnetic Laplacians, integrated density of states, the connection between magnetic Laplacian and the Heisenberg sublaplacian, the Bérézine transforms attached to this generalized Bargman spaces, and a formula given this transform as a function of the Laplace operator, the composition of this transform, displaced Fock states attached to this magnetic Laplacian, and next I will move to another subject, which is the potential of confinements, and I will talk about another kind of Hamiltonians, which are called the Fock-Darwin Hamiltonians. We'll talk about reproducing kernels also to attach it to this Hamilton, to the levels, Fock-Darwin levels, and at the end I will talk about heat equation for these Hamiltonians. So spherical harmonics. So I think that people are working in Cn, this high dimension. They know what are these polynomials that are this restriction to the unit sphere of polynomials that are harmonic with respect to the Laplacian of Cn, and which are homogeneous of degree p in Z and Q in Z bar, and their notation of these spaces are HPQ. They are the analog of the exponentials function for the Fourier series when we are working on the complex plane. So the analog of this exponential are the spherical harmonics in Cn. And those spaces are finite dimension spaces, and their dimension is given by formula 4, and in which the ingredient here is given by formula 2. So more information can be seen in reading book Function Theory on the unit ball of Cn. Now, magnetic Laplacian on Cn. I will start by a simple operator, which is known as the Landau Hamiltonian operator in R2n, which is given by this expression in yellow. I'm not adding any potential, so I suppose that the potential here is 0. And the effects of the magnetic field, and the magnetic field of strands which is proportional to B. And then when we perform an intertwining relation between with this operator in X and Y variable with respect to this ground state transformation, which is the unitary map from L to R to N to L to Cn, we get this expression in the Z variable and Z bar. Of course, you wonder if you add some potential here, we may have some effect here. We can, but this is another story. But for us, for the moment, it's just that we put B equal 1, and all physics units, all physics constants are put to 1. And then the operator delta tilde at the end of this slide is what we call the magnetic Laplacian, because it's like a Laplacian operator plus this Euler operator, Z bar D bar of Z D of and D bar. So this is what we call the magnetic Laplacian. And the property of this operator are well known. It is unbounded symmetric operator on C infinity 0 Cn, essentially self-adjoint. The spectrum consists of eigenvalues of infinite multiplicities, and these eigenvalues are positive integer numbers. So this is why we are making simplification of all physics constants in a way that eigenvalues are just these numbers, 0, 1, 2, etc. And those are called Landau levels, because this magnetic Laplacian is just the intertwined form of the Landau Hamiltonian in R2n. So we keep saying that this is eigenvalues are Landau levels. Now, generalized Bargman spaces or Cn. In 1997, we introduced the class of generalized Bargman spaces indexed by integer numbers as eigenspaces of the single operator delta tilde in this way. And we proved that when we are in this first Landau level, m equals 0, that this eigenspace turned out to be a realization by harmonic function with respect to delta tilde of the classical Bargman space, whose elements are Gaussian analytic, Gaussian square integrable analytic function. It means that when m equals 0, this space is just the Fock-Bargman space on Cn. So this result was published in this paper in Compte Rendu of Academy of Science of Paris in 1997 with one of my colleagues in Beni Mellal and another colleague, which was our supervisor, Professor Ahmed Intisar from Rabat. And what we have done is that we were able to write an explicit expression for eigenfunctions of this space, element of this space, in terms of an orthonormal basis of spherical harmonics of Cn. So this is the Fourier series of an element of this generalized Bargman space. And these notations means this quantity, and dnpq is the dimension of the spherical harmonic space, HPQ, and HGPQ is an orthonormal basis. So from this explicit expression of description of eigenfunction of this element, we are able to exhibit an orthonormal basis. And using the connection between confluent hypergeometric functions and Laguerre polynomial, when the index, the first is a negative integer, this is a polynomial, we are able to write this expression of an orthonormal basis of this space, E to M of Cn, for P varying and Q varying to M and G to the dimension of space of spherical harmonics. So these functions are our principal tool to compute the reproducing kernel by using the Zaremba formula. In fact, at this time, we didn't use the Zaremba formula directly. We have used some invariance property of the group and the semi-simple group, semi-direct group of UN and Cn. But here we can use directly the Zaremba formula. And the Zaremba formula is an old formula, and it appears first in 1907 in this journal of Bulletin International de l'Académie des Sciences de Cracovie. Here is the journal. Here is the paper of Zaremba, And here is the first formula for the reproducing kernel expressed in terms of an orthonormal basis of the space. But it is presented in this way. In 35, if you can see that is the reproducing kernel property. So now reproducing kernels, we have just to do this computation of use Zaremba formula to get that the reproducing kernel is given by this Laguerre polynomial for this eigenspace. So, and we use the explicit expression for the orthonormal basis, and then computation, and some point the proof we see that we need this expression of this orthonormal basis of spherical harmony. In fact, the key behind this computation is the Kornweider formula for the spherical harmonics. I mean, like another Zaremba formula for this spherical harmonics. Here, the formula is very known, and it is given in terms of Jacobi polynomial, and then we can put some change and then involve Zernike and disk polynomials, etc. And another K formula is another Kornweider addition formula for the Laguerre polynomials in terms of these disk polynomials, and this was given by Kornweider. And then at the end, we get the reproducing kernel of this space. So when we put m equals 0, you will find the reproducing kernel of the Bergman space of Cn. So some application of this result is that we can rewrite Laguerre polynomials in terms of derivative of Laguerre polynomials in separate variable and the dimension Tnpq of the spherical harmonics. This is some kind of application of. So now the height and wave equations. So we can solve the height Cauchy problem with this initial condition, and this is the explicit formula for the height kernel. So if you want to prove these things, you just need to use the reproducing kernel, I mean, this projection. And then what is crucial here is that you are able to compute the series. This is the spectral theorem, the discrete resolution of the height semigroup. And then here you have eigenvalues in M, and then reproducing kernel. And you use the generating function of Laguerre polynomial. That is the trick. So this is the key idea, is that you use the generating function for Laguerre polynomial and reproducing kernel, and then this formula for Laguerre polynomial, and you get the result. And also, of course, this kernel should be understood in the distributional sense. The same story, you can also use the reproducing kernel and the function given this the solution for the wave. And here the m, the integer m, are the eigenvalues. This is a kind of spectral theorem for this function of the operator. The height, the wave semigroup. And until now, we don't have a closed formula for this wave kernel. So if somebody is interested in that question, that will be nice if we can succeed in writing the closed form for this series. But I mean, we can do a lot. Another game is that to write this term in terms of this Laplace inverse transform and get the an integral representation of this wave kernel in terms of the G function, which is the trichomy function that our colleague is just talking about in the Whittaker transform. This is the the G or psi, depending on the books. So if you want more information about the subjects, so this heat and wave and reproducing kernel, so you can see this reference in Journal of Mathematical Physics in 2000. So Ahmed Intisar passed away in 2017, and I mean, he was a great person, great professor, and he did a lot of things, and he was making a lot of contribution and encouraging some mathematical analysis with in connection with some physics. He was very open to these things. So this is just to have some thoughts about this great professor. Now, a spectral decomposition of this magnetic Laplacian. So the same story, once you have this reproducing kernel, so you do this projection onto these eigenspaces, and then we are able to write the spectral projectors. And here, in terms of we have not exact degree, but say this function of the greatest integer not exceeding the integer parts of the number lambda. So the proof is essentially use this projection on this eigenspace and be able to do this summation of Laguerre polynomials. And when we do this summation of reproducing kernel, which is based on the summation of this Laguerre polynomial, we get the kernel of the spectral projection. So it seems that at any time we want to do something with this operator like spectral theory, there is some formula for Laguerre polynomial somewhere that is there to solve the problem. It's like there is a word of orthogonal polynomials, Laguerre polynomial, that are behind the point we want to solve. So here, remark that this is formula of Laguerre polynomial that solve the problem, spectral projects. And from there, you can get the exact an integral representation of the integral kernel of the resolvent operator in terms of the Tricomi function. So this is the Tricomi function, and then you can. So the proof is simple. This is in the theory. You connect the resolvent with the spectral projectors, and then you do computation. That's it. And this computation, you see that at some point you have a summation of this Laguerre polynomial, and then you use some formula for this series of Laguerre polynomials, and then you get the resolvent kernel of the magnetic Laplacian and Cn. So each time you get there is a formula of Laguerre polynomial that solves the problem. So I will skip these details, but if you want more information, here is the paper dealing with this resolvent kernel and spectral projector, this Journal of Mathematical Physics. So with my colleagues in Beni Mellal. So now something I want to talk about is this integral density of state. So you take the Hamiltonian operator and then you restrict it to some domain omega, and then you compute the number of eigenvalues less than the lambda, and then you do this ratio, and then you push the limit when your domain is going to the whole space, and this is called the integral density of state. There is another formula which are very convenient for us, because we will use the projector operator, the spectral decomposition, to compute this integrate density of state. So this is a kind of, this IDS is an average of the kernel of the spectral projector operator. It was pointed out by Stricker in a paper called Spectral Asymptotic Revisited in Journal Fourier Analysis in 2012. And this is the substitute for the first one, definition one, and this definition was motivated by the well-known Weil asymptotic law, that this number of the cardinality of these eigenvalues is a constant volume of omega for when the Hamiltonian is the free particle Hamiltonian is a Laplacian on a compact domain with this smooth boundary, with Dirichlet or Neumann boundary condition. So now, this spectral function, we can, we just now to compute this IDS, we just need to compute this expression when we have those eigenfunctions, and then if you are able to write a compact formula for this, so that we can integrate over the diagonal of this, and then we get the IDS. So now the Radon-Nikodym derivative of this IDS is the DOS, and this DOS can be exploited in the case of Landau Hamiltonian to measure in the gap between Landau levels energies of new states that could be created if a random potential is added. So there are people in physics that want to add some random potential to the Landau Hamiltonian. The first one I show you in R2n, and see if there is some in the gap between Landau levels, if there are energies of new state. So they need this dose. And here is a reference for people who want to learn more about this, the integrate density of state for random Schrödinger operator. In this, I think it's a review paper. So now, in our case, we can compute these things because we have this spectral function, because we have this spectral projectors. And here it is given in terms of the integer parts of lambda. And now we compute this diagonal, and we use this expression of Laguerre polynomial at zero, at the origin at zero, and then we get this expression for the integrate density of state of magnetic Laplacian. And when we take the particular case for a complex plane, then the integrate density of state become more simple, which is pi to the power minus 1 plus the integer parts of lambda, which correspond by changing some notation to make things, with the work of Nakamura, and this is exactly the result that Nakamura found in a paper he wrote in 2001, and the title is a remark on the Dirichlet-Neumann decoupling and integrate density of state, Journal of Functional Analysis, and who derived it by proving that it was independent of the choice of the boundary condition. So I think that this computation in Cn is correct. Okay, so now the connection between the magnetic Laplacian and the Heisenberg sublaplacian, and for the Heisenberg sublaplacian, which is given by this expression in terms of derivative of t and z bar, and the connection between this operator and the magnetic Laplacian is this formula. You just need to use the Fourier transform with respect to the variable t, and combine it, intertwine with this transform tau lambda, and then you get the magnetic Laplacian from the Heisenberg sub-Laplacian. So this is the connection, and with this connection, you can now write the resolvent kernel for the Heisenberg sub-Laplacian. So we have done this connection and this formula because we didn't find the resolvent kernel for this Heisenberg sub-Laplacian. I mean, a lot of people are talking about the Heisenberg sub-Laplacian, but we didn't find at the time the explicit expression for the resolvent kernel for this operator. So we derived this expression from the magnetic Laplacian on Cn, I mean from the Landau Hamiltonian. So if you want more information, you can see this reference, Electronic Journal of Differential Equation in 2002, when you have this relation and this another application that the green kernel for some fractional power of the core Laplacian. So now, what the things it is also interested is that in this resolvent kernel integral representation, if you look to the limit case of zeta equal 0, and you do the computation, and I have done this with my colleague Ranmi, and it is a preprint in arXiv, and we start from this integral representation of the resolvent kernel for the core Laplacian, and we found that at the zeta limit 0, we recover the fundamental solution of the Heisenberg sub-Laplacian. This fundamental solution was already found by Folland in the reference I showed before. In Bulletin, I think it was in Bulletin American Mathematical Society. Yes, and then yes, we this means that now the fundamental solution of the Heisenberg sub-Laplacian come simply from the magnetic Laplacian on Cn, or if you want from the Landau Hamiltonian on Cn, we do direct computation with spectral theory. Like you don't need to know harmonic analysis, I think. You don't need to need harmonic. To find this fundamental solution. It's a limit case in this formula. Another thing is that this fundamental solution of Folland can be represented in terms of the Tricomi function, the Tricomi G function. This is a small remark. And then once you have this spectral function for the magnetic Laplacian, you can now get the spectral function for the Heisenberg sub-Laplacian from the magnetic Laplacian, and then you can compute the integral density of state for the Heisenberg sub-Laplacian, and it is given by this kind of formula. It's gamma n lambda to the power n, and gamma is given by this series, and this series it's not simple to get closed form for this series. If somebody is interested in the subject, it's okay. If you can get, even in some particular case of the dimension n, what is exactly this constant? Maybe it's connected in some particular case to the zeta function or Riemann zeta function. Okay, now the Bayesian transform. Once you have a reproducing kernel, so you can construct this story of Bayes ensemble and with the reproducing kernel, and then you use this top list operator, you combine them, and then you compose them, and then you get the Bayesian transform. And if you want to go fast and use directly the Bayesian kernel, it's this formula using the reproducing kernel, which we can use. But in fact, the kernel of the Bayesian transform is the result of quantization, dequantization with respect to a set of coherent states. This is the more general way to see the kernel. But if you want to don't enter into the story of quantization, dequantization, and physics, and you want to write the kernel, so use the reproducing kernel in this form and call it the Bayesian kernel. And for our generalized Bargman space, this Bayesian transform is in this form. It's a kind of convolution with this function over the group Cn. So now, one of the important questions that was raised by Bayesian himself is how to write the Bayesian transform as a function of the Laplace-Beltrami operator of your phase space. Because this question of writing the Bayesian transform as a function of the Laplace-Beltrami is the point that enters into the story of called the correspondence principle. Correspondence principle, that means that this bracket between quantum observables that are operators in the semi-classical limits, as h bar goes to 0, you have to recover the Poisson bracket between classical observable, quantum observable, the bracket between quantum observable at the semi-classical limit should go to the Poisson bracket between classical observable. And there, inside this story of correspondence principle, the people need to write the Bayesian transform as a function of it's a kind of hyper-differential form of the operator B0 Bayesian. So in our case, we can extend the Bayesian result to higher Landau level, because our Bayesian transform is a convolution against this function Hm. And if you use the theory, you just need to compute the Fourier transform of the function Hm and evaluate it at this 1 over I, the gradient. And if we can do this computation, this is what we found. We found that the Bm is the exponential as for m equals 0 times a polynomial function of the Laplace operator, with the explicit expression of the coefficients given in terms of this 3f2 hypergeometric function. So I will skip the proof because it's very technical. So we have to write the Fourier, we have to write the linearization of the products of Laguerre polynomials, and then do this computation, etc., etc. And if you want more information, you can look to this reference in Journal of Fourier Analysis and Application. And in this reference, it is the detail of this formula, and also the details about the reproducing kernel that I re-derived it using Zaremba formula directly because we know the explicit expression for the orthonormal basis of this space. So now we can decompose also this Bayesian transform into small pieces by using a kind of a linearization of the square root of the Laguerre polynomial, and we can see how it becomes more simple, and then we can see its action on L2Cn by decomposition in the radial and angular parts. and using Frank-Hicks formula and get something like that. But if you want more detail on this decomposition, so we have some paper in 2008 about the decomposition of magnetic Berezin transform on CN. So, right now I will move to this displaced Fock states attached to this operator. So these displaced Fock states are important in quantum theory, and these are, this displacing this Fock states are Fock states are like number states, are eigenfunction of the harmonic oscillator, and then you act on them on an operator, which means mathematically you are acting by an operator of some representation of some group. For the case of the harmonic oscillator, the group is the Heisenberg group, the Weyl-Heisenberg group. So let us see in our case what is this displacement operator. So our magnetic Laplacian decomposes in this way on A and A star and A joints, and then the displacement is given by this formula here in yellow. So now you just have to take a Fock state, these monomials, and compute the action, and you get this formula. Okay, so now you have this displaced Fock states. So what you can do with these things? So what you can do is, I will skip the proof of this computation. It's used essentially the Bacher-Hausdorff formula and direct computation. So the unity of the generalized Bargmann space, I have a difficulty to pronunciate this space. Anyway, so the unity can be solved in this way in terms of Dirac bracket notation. And these things, it seems very, very simple. The identity operator decomposes in this way, and here alpha is a multi-index. And when we see the proof of this result, somewhere in the proof we need this summation formula on Laguerre polynomials. And this is the key ingredient in this proof. So in some sense, this QMZW is up to a conjugation of some pi to the power minus n. This is the reproducing kernel. And when we look at this formula, first of all, if you want proof of these things, this was published in this paper in China's Physics Later in 2002. But now, why I am talking about this stuff? Because now, when I try to reread the proof, what I can say that the reproducing kernel of this generalized Bargmann space decomposes in a small kernels that this may be also reproducing kernel for something we have to write correctly. Maybe against spaces of some correct, you have to find some correct way to write the exact operator and the eigenvalues, but it decomposes in this way. And this is small reproducing, for the moment, I cannot say reproducing kernel, but kernels are exactly the kernel that recently a colleague from Tokyo, from Keio University in Japan, Professor Makoto Katori, just was taking about the correlation, what he called the correlation kernel to define the extended Heisenberg family of determinantal point process. You see, 2022. But so, in fact, the kernel he chose to extend the Heisenberg family, the Ginebra one, is in fact, these kernels are natural and they are contained in the reproducing kernel of the spaces we are talking about for the eigenfunctions, space of eigenfunctions for the magnetic Laplacian. So here is a picture from his paper, and when you see the kernel he is using is exactly what comes from the proof of the resolution of the identity in terms of displaced Fock states. So how these displaced Fock states are very simple, but they lead to some natural extension. So this first kernel here is the G-neighbor one. I mean the exponential Z W bar or Z scalar product Z and W. So now I will move to the last part, is the potential of confinement. So when you restrict the motion of a particle in one dimension, you call it a quantum well. But if you restrict the motion of an electron in all directions, you call it a quantum dot. I mean, this is a way of making a model of artificial atoms or molecules by putting a potential called the potential of confinement that satisfy this condition that V of xy go to infinity as xy go to infinity. So an example of this is this parabolic potential. Okay? So now these quantum dots, which are now, if you put this potential, you can imagine that you are creating artificially a molecule or something like that has many applications in quantum information and in bioimaging and in medicines and etc. And more recently in this story of illumination. And for this story of size-dependent absorption and emissions, there was a Nobel Prize in chemistry about quantum dots. So it was awarded for 3 scientists from the United States for the discovery and synthesis of quantum dots. So meaning that is a very interesting subject to study the mathematical behind this the Hamiltonians behind. So for a quantum dots, an artificial stuff with n electrons, this is the form of the Hamiltonian, and decomposed in a small Hamiltonian, and the Coulombian W is a Coulombian interaction. And you see in the decomposition of each one, there is another small pieces which is orbital, and plus something depending on the spin and another concept. But if you see the orbital one is exactly the Landau Hamiltonian plus now a potential V of x and y. So this is why I was telling you in my first slides that I have adding 0. There was 0 potential. And now there is a discussion. If you neglect the Coulombian repulsion between electron or not. So if the interaction is ignored, so the model of the Fock-Darwin spectrum, it works. But when the interaction is taken into account, the picture has to be modified. But for a quadratic confining potential like x squared plus y squared, the Fock-Darwin spectrum continues to apply to the center of the mass, the motion of the center of the mass. So meaning that our
So Jair, sorry, can you hear me?
model will be this one. I mean, our magnetic independently in 1928 and 1930. So it is very old Hamiltonian. Now, everything is known in the physics of, not everything, I mean, but the spectral things, eigenvalues, eigenfunctions, and the multiplicities are finite. It's not like Landau levels. And if we write the eigenvalues in a very symmetric way, and we say that this constant, I mean, this is what we call physicists the hybrid frequency, omega plus and minus. And if this ratio go to zero, meaning the magnetic field is so strong in comparison with the constant controlling the confining potential, then the Fock-Darwin levels go to Fock-Darwin levels go to Landau levels. So this is the remark, but important way to write the Fock-Darwin levels. Now, let us do some mathematics about this operator. In R to N, we can write this operator in this way by equation 1. We can do the same game, I mean, intertwining this operator to write it in a complex way, like magnetic Laplacian. And you see now that we are adding the conjugate of the Euler operator in the magnetic Laplacian. That is the difference between the two operators. But I mean, spectral properties are also different. I mean, we can write explicit expression for the eigenfunction in using spherical harmonics, and we have to discuss some condition between the omega, the constant controlling the confining potential, and the constant controlling the magnetic field. So we can do these things. We can also do another form to intertwine the operator in order to represent it just simply in this space, L2Cn with the Gaussian. And then these constants before these Euler operators have the property that their sum is equal ones. So it's we can make things more simple. And now we can study the spectral property and prove that eigenvalues of this Fock-Darwin Hamiltonian is of this form, and each eigenvalues is of finite multiplicity, and the spectrum is a pure point spectrum, etc., etc. We can also write, expand this L2 eigenfunction in an orthonormal basis in terms of spherical harmonics. But here we have this to discuss some rationality or not rationality of this ratio. So we have not
So Javier, sorry, can you hear me?
Another problem, which is arithmetical eigen for each eigen Fock-Darwin level, and depending of this rationality. So if you want information about this problem, you can see our paper in Physica Scripta in 2003. There is the detail of the mathematical work. So the spectrum is only Fock-Darwin levels, and this operator has a compact resolvent. But I don't think that even the operator is very old. Even when I don't think that problem. Yeah, when we move to Cn, we have to use this machinery of spherical harmonics. Okay, but I don't think that there is a result about what is the exact formula for the resolvent kernel of this operator. I never see anything about this operator, even it is an old operator. So if somebody can tell me or can tell me if there is a formula for the resolvent of this operator, we can prove that is compact resolvent. But what is the formula for this resolvent operator, resolvent kernel? I will push things more than that. I will give you the H kernel. And if somebody is able to compute the Laplace transform, it's okay.
So now,
sorry,
yes. Can you hear me? Can you hear
me?
No, just a question. How much time do you think that you need to?
I need
finish the talk?
5 minutes
Okay, thank you very much.
because I am at the end.
Okay.
I am at the end. So the same story. You have we are able to compute eigenfunction an orthonormal basis of this space. Okay, we are able to do that in terms of Laguerre polynomial and spherical harmonics. And once we do that, we use the Arima formula, and then the same story will appear. Kornweider formula for spherical harmonics, and now we have exact expression for reproducing kernel. And this reproducing kernel, depending of this rationality of this coupling of this depending on magnetic field and the frequency controlling the parabolic potential. So the same story. So anyway, we have explicit expression for reproducing kernel. So now I will skip the proof. Now just the H equation. Let us take the complex plane and write in dimension 1 the Fock-Darwin. Very simple way. We can get the H kernel. I already do this computation. But I didn't use mathematics. I mean, I didn't use because reproducing kernel here is so the expression is complicated. It's not like the magnetic Laplacian. I use subspectral theory and then I get the H kernel. No, I will do another story. I will move to the classical mechanics, write the Lagrangian function associated to this magnetic, to this Fock-Darwin Hamiltonian, and compute the action in terms of the Lagrangian function. And once I have the action, I compute the Hessian of this Hessian matrix and the determinant, and I will use a very old formula in semi-classical, called the Van Vleck Pauli formula. And it is the formula on the bottom of the slide. I mean, you have just to prepare this ingredient. And here, the formula appears in a paper of Van Vleck in 1988. And the formula is given by equation 11. If you read it correctly and you apply it, it's okay. You can get the H kernel. This H kernel, you can get it directly without using, partial differential techniques or Fourier, nothing, or reproducing kernel or anything like that. So the paper appeared in Van Vleck in 1928. This is what I want to say. And now for higher dimension, you can make some tonsorization, and then you get an explicit formula for the H kernel of this Fock-Darwin Hamiltonian, but not able to compute the resolvent kernel here. So when in a particular case, when we kill the confining potential and we put the magnetic field on one, we recover the H kernel for the magnetic Laplacian I already showed you. We can also compute the trace for the semi-group of this Fock-Darwin Hamiltonian. So just add, before finishing I want to tell you that there are some conferences in future. In 2025, there will be ISAC Congress in Kazakhstan. And if you are interested in the session of integral transform and reproduction kernel, feel free to contact me. Also, feel free to become a member of ISAC. And in 26, there will be conference, international conference on mathematical methods in physics in Marrakesh, Morocco, from 2025, April 26. This event is associated also with ISAC. And all information will be communicated late on April, I think. So thank you very much for listening.
Okay, thank you, Suhair. Thank you very much for your very nice talk. At this moment, we are open for questions. Does anyone have questions for Suhair?
Maybe I have used more time? No? More than 1 hour?
I think it was 55 minutes, which was in the normal range, I think.
Thank you. 55, okay.
Right, it was not... Maybe I have a question, Suhair, because at some point you compute explicitly with very specific functions, the fundamental solution for the sublaplacian in
Yes.
the Heisenberg group, right? And then
Yes.
you said that you recovered the fundamental solution that computes
Yes.
Folland, right?
Yes.
Folland. How much structure of the Heisenberg group you use in this formula? I mean,
What?
are you using a specific structure of the Heisenberg group in computing
No.
this fundamental solution, or you
No,
can
I'm not
extend this
using
to
nothing. I'm using nothing. I have here the resolvent kernel of the Heisenberg sublaplacian. Okay?
okay,
You put zeta equals 0 and you do the computation. That's it. In this
Okay.
integral.
okay,
You have to manage, but if you see, there is a lot of computation. It is not immediate. It is a lot of computation.
computation, right?
Yes, it is a pre-branching archive I can send to you. But at the end, when you put 0, you get the GF, the fundamental solution at this composition,
Okay.
which is the exact formula with the exact constant.
Okay,
The
okay,
exact fundamental solution of the sublaplacian, just from the resolvent kernel in its integral representation form. You put zeta equals 0 and you push computation to the end,
okay.
and
Yes,
you
sir.
get the solution, the fundamental solution.
You get the fundamental solution. Okay,
And this this resolvent is coming from the resolvent kernel of the magnetic Laplacian. By this intertwining relation between the magnetic Laplacian and the Heisenberg sublaplacian. This is the story.
okay. I have another question, but maybe I will email you. Okay,
Yes.
because our next speaker is with us. Okay, so thank you very much, Professor Sohair Moan from Morocco.
Thank you.
Morocco.
Thank you.
Thank you for accepting our invitation. It was a pleasure to have you in our conference. Then maybe you can stop sharing your screen. And okay, just let me ask Julian from technical support. Okay, all right. So, dear attendees, thank you very much for joining us. It's really a great pleasure for me to introduce Professor Jirair Avetisyan from the Ghent Analysis and PD Center. As you know, Jirair Avetisyan will give the Ekman lecture for this conference. The Ekman lecture usually is not a lecture about mathematics, but is more related with the impact of mathematics in different communities. And today, in this spirit, Jirair Avetisyan will talk about the challenges of running an international research group in a developing country. So, Jirair, thank you very much for accepting our invitation. It's really my great pleasure, our great pleasure to have you today in the conference. Thank you.
So thank you very much for the nice introduction. And indeed, good afternoon, dear colleagues, dear attendees. It is a pleasure to speak at this conference. And first of all, I again want to reciprocate with gratitude towards the organizers for giving me this opportunity. Indeed, so my task is to speak about challenges of running an international research group or international mathematical research activity in a developing country. So I'll be mostly talking about challenges, which are negative things, but I won't be speaking about the gratifications, the positive parts, leaving that to the audience, if you wish, or another occasion. So indeed, so I want to speak about some of the challenges which I think are typical of developing countries. Of course, most of the challenges of running a research group are so universal, they are the same in every country, but some of them are more typical of developing countries than others, and I'll try to concentrate on them. Normally, by saying a developing country, there is no strict definition of it. So, say in this context, let's understand a developing country like a country where either a country which either does have serious, say, mathematical traditions, but does not have is not financially very well to do, is not among the richest countries, let's put it that way for simplicity, or countries which are financially well to do, but maybe don't have formidable mathematical traditions, or both, right? So my personal experience comes mostly from the country where I come from Armenia, from some other countries like Russia, where I have worked. So from my perspective, but generalizing to generally developing countries, hopefully this will resonate to some other colleagues of mine who work in developing countries as well. All right, here is more or less the structure of the thing. First, I'll speak about the remote lab a little bit, the lab that we established in Armenia. Then I'll speak about 5 broad categories of challenges, which are, well, funding, bureaucracy, attracting and retaining talent, facilities, and integration. So let's begin with the remote lab. And here is basically the short history of the lab. The Ghent Analysis and PDE Center, headed by Professor Michael Różański, where I also work at together with Tuvan. Last year, we established a remote lab in Armenia, basically a team of 10 researchers at different levels. And this was made possible by 2 research grants, each about 400,000 euros, programs for 4 to 5 years. One of them is from the Higher Education and Sciences Committee of Armenia, basically a government organization, and the other one is private funding, the FAST Foundation. So these are correspondingly 2 research teams, 5 researchers in each roughly, One of them is devoted to analysis on groups and harmonic analysis, and the other one is singular PDEs, very weak solutions, etc. Right, so this is an interesting format of the grant. It was championed first years ago by the FAST Foundation, this private foundation. They began allocating funding for research teams which are supervised by foreign researchers remotely. So it is a team of researchers with or without a local coordinator in place, say in Armenia, and there is a prominent scientist from abroad who remotely supervises the team, spends sometimes several weeks per year in Armenia in person, but otherwise it's mostly remote. So, and then the Higher Education and Science Committee, basically the government's main body responsible for basic science, took over this model with slight modifications. And for some time, both of them have been providing these grants. Although I have to say that this year, the FAST Foundation has decided to cease the program, and all projects formerly funded by FAST Foundation, including one of our projects, were again transferred to the Higher Education and Science Committee. So, but this is an interesting model where you know that there aren't as many highly qualified research supervisors in your country or in your region, and you allow through this format to create new labs, new teams remotely with a remote supervision. So here is the structure of our team. Basically, we have 3 faculty members from Yerevan State University. That's what YSU stands for. We have 2 postdocs from Iran. We have 2 PhD students from Armenia and 3 master students from Armenia. This is the structure. Okay, so let's begin talking about challenges, and maybe the first challenge that comes to mind when talking about developing countries is funding. So what's about it? So the first challenge with funding is that, especially when it comes to basic sciences, it is often too little until it is too late. So what do I mean by this? Well, a senior colleague of mine and a friend, a professor of theoretical physics in Yerevan, usually says this. He says, if you see a particular government investing heavily in basic science, that's a sure sign that maybe basic science is already dead in that country. I mean, this is a little bit tongue-in-cheek, but the lesson is that often governments are reluctant to invest sufficiently in basic science until it is too late, until the basic sciences are at a critical point of breaking. So, say if you look at countries like, also including developed countries like Spain, Portugal, Italy, or also Greece, these are countries which have good traditions in basic sciences, and they still have remarkable activities in basic sciences, but these basic sciences are underfunded. Whereas in countries like Armenia, Russia, Kazakhstan, Uzbekistan, where you see in recent years a remarkable increase of government spending in basic sciences, you can't help wondering if this is not too late, because, say, in Armenia, the statistical average age of a researcher is over 60. So let it sink for a moment. The average Armenian researcher is retired. So it is in this situation that the government finally decides to act. Right? So, and this is unfortunately typical for many developing countries. And once funding becomes available, then it is absolutely necessary to act upon it, because otherwise it may be really too late. So another problem with funding in developing countries are formal salary caps. Say, academic salary grades exist in many countries, especially in Europe, even in the UK, although the universities are private mostly, but still you have these grades and spine points and so on. So basically, it's hard to keep the salaries competitive. And there is this mentality, especially I can speak about Armenia, but probably this is similar in many other countries, that the government says, well, you are funded from the budget, state budget, exactly the same way as high school teachers. And how can we increase your salary if we can't increase the salaries of high school teachers? And high school teachers are too many to increase the salaries right away, right? So, and with this kind of social justice mindset, it is very hard to compete for talent, because, as I'll come back to it again, because unlike high school teachers, which usually have just pedagogical education, the researchers in mathematics, they have all the good skills to become very successful engineers and data scientists and so on, and you are competing with a different employment market. Okay, and then the third challenge is the limited variety of sources. This is especially true about small countries and including developing countries. Say, if we talk about the United States or the United Kingdom, there are so many different foundations and associations and funding bodies which offer different kinds of grants, right? You can get funding from different sources. There is a variety of sources, potential sources. But when we speak about Belgium, although Belgium is a pretty rich country, but a small one. And then what are the main sources of funding basic science? It's basically, in our case, it's Flemish government. Okay. So, and then of course the European Union, but then it's highly competitive to get the European Union grants. So in case of Armenia, it is very similar. So I told you there are two basic sources. The first one was the State Committee for Science and Higher Education. And then there was the FAST Foundation, which this year seized the program, and now it's just the government, and that's it, right? So, and this is then a serious limitation. And finally, I want to talk about a little bit about, not maybe to talk about, but to mention traditions of austerity, so to speak, because somehow in many countries, especially developing countries, there is this inertial mindset that scientists should be poor for some reason. That when someone, if you talk about someone who is, say, an engineer or a doctor, and they say a doctor makes, say, 10 operations a day and earns a lot of money, everyone says good for them. They are working more, they're earning more. But for some reason, when a certain scientist then wins too many grants, then people start to look at it with suspicion. He's a scientist, he shouldn't be getting that much money. Okay, so this is kind of a tradition which is not always constructive, let's put it that way. All right, so the next category of problems that you run into is related with broad term bureaucracy. And the first thing I want to mention is the anti-corruption laws. Okay, I mean, in my experience, the more corruption there is in a country, the stronger the anti-corruption laws are. I don't know if these anti-corruption laws actually help against corruption or not. I don't know. But what I know is they make your life very difficult. So for every little operation, you need permissions and the whole bureaucracy and so on and so forth. It becomes very hard. And eventually, certain operations are simply not being done because they aren't worth the bother. Then another aspect of this is what I call a dissipation of responsibility. This is when the bureaucratic machine isn't prepared for certain categories of operations. It just never happened to them before, and they didn't cross their minds that this is something they should do. And when the time comes to do it, no one knows how to do it, and no one knows who is responsible for doing it. Right? So you need to do a certain thing, a certain operation, and you talk to someone, you are looking for someone who would help you doing it. It turns out there is no one who has the responsibility for that. They say, okay, let's call to this one, let's call to that one, and then talk to this and that, and then eventually you are stuck, nothing is being done, and there is not a single person who is responsible for that failure. Right? So, and no one is responsible is the correct phrase for many situations in our experience with the remote lab in Armenia, honestly. Then, of course, resistance to modernization, which is like bureaucracy is always conservative, but maybe it is more so in developing countries. The bureaucracy is trying to do the things the way they've been doing for years, and although many of them do know that things have changed, that times have changed, but they don't want to invest the energy and efforts to change the ways things are done, and no one forces them. So it's a hard situation for someone who is trying to make things more flexible, more efficient. It's basically resistance. And then there are certain, I call them unhealthy and costly restrictions, either by rules or habits. So written rules or unwritten rules, which are basically habits, sometimes disguised under the rules. So everyone tells you this is a rule until you discover it isn't. It's just a habit. Right? For instance, when I worked for a short period in Russia, then I attended a conference, and I was supposed to be reimbursed for all my transport and travel expenses. And these travel expenses included a pretty expensive taxi transfer from the airport in the middle of the night. And then I tried to get a reimbursement for that, and in the respective department, they told me, we are not doing that. I said, what does it mean? Here are the rules, and here it says, well, if taxi is being taken during the nighttime, then it is eligible for reimbursement. They said, yes, it's written, but we are not doing this. Okay. So just because they've never been doing it, and the locals don't resist. And when you're alone in that, the locals, they were born in that, they were raised in that, they never seen anything but that, so they don't resist. It's only you trying to kind of fight the windmills. Sometimes it's hard, and then sometimes your researchers or you have to pay for things which you shouldn't. And sometimes it's also because of that. It's also the case that you have to do unhealthy things. Okay, so now let's talk a little bit about attracting and retaining talent, which is a critical aspect for running a mathematical research team. So maybe one of the saddest, from my perspective, aspects is the very pragmatic mindset of people in developing countries. So you see, you often get these bright students or young researchers who are coming from families which have been in financial trouble for years. So they were raised in financial trouble, and in developing countries, there are many families with financial troubles. And the main thing, kind of the main program that these young, bright people bear in mind is getting out of poverty at all costs and nothing else. So it's very hard to talk to them about other aspects of quality of life. Say, okay, you may not earn twice as much, but your life may be more interesting. You may be doing more meaningful for yourself things, for more entertaining, more fulfilling in many aspects. In a sense, these guys come from their families with a program to get rich. And academia is not the right place to get rich, honestly. So, and then I'm gradually coming to the next line, which is competition with tech industry, especially if you are somewhere like Yerevan, which is full of tech industry, IT companies who are trying to attract bachelor students for positions in software development and engineering, and offering bachelor students salaries which are higher than full professor salaries in the university. It is very, very tough to get these students stick to academic careers. And here I'm going to the next line already, especially since the academic careers are not very appealing, aside from the innate kind of attractiveness of academic job itself, like the mathematical research is interesting, it is fulfilling by itself, but from other aspects, be that the quality of life, be that the quality of workspace or whatever, the academic careers in developing countries are not very appealing. And all these three aspects together make it very challenging to acquire and to retain talent, especially young talent. All right, so let me go to the next category of challenges related to facilities. Well, it is understandable that less affluent nations are lacking in facilities. Facilities cost a lot of money. But sometimes there are some unnecessary extremes. It is, I talked about it a little bit before, maybe I can repeat it, that there is a tradition of unhealthy parsimony that the scientists and mathematicians included, especially basic sciences, they should be parsimonious in all ways. All right. So these facilities in which you work, it can be just the building, it can be the office appliances, it can be your chair, it can be your table, it can be the heating, it can be whatever. They are old-fashioned at best, but often actually unhealthy. Actually unhealthy to the extent that sometimes there are serious health concerns for some. This is not often, but sometimes there have been some cases where there were serious health concerns for employees, and the university doesn't have a solution to that. And the question even is not being raised because everyone seems to be kind of content with that this is parsimony, you know. So this is an unhealthy level of parsimony, let me put it that way. Then the second point is atmosphere not very conducive of deep work. By this, I mean that not every university has an appropriate, say, academic park or a campus. Say, the Yerevan State University is right in the middle of a big city, and there is a lot of noise around. And the offices of researchers are situated in the same corridors as the lecture rooms. And you can imagine that in the morning hours, how noisy it is, right? With random students opening your door every here and then. So overall, so this is again a problem with facilities. That the environment where you work is not always very conducive of deep and concentrated work. And then all of this given, there is a certain unwillingness to raise the standards. So say the administration and the leadership, they understand that there are these problems, but maybe they are willing to change things. It's just that we are not observing any big steps towards it. So at least from an observationalist's kind of point of view, you see an unwillingness to raise the standards and to try to catch up with the developing countries very often. All right, and finally, I want to talk about the problem of integration, and by integration, I mean integration of international researchers in the host country, right? Because I stress that this is about international research group in a developing country. Developed countries, almost all of them have a long history of welcoming international workers from around the world and accommodating them. There are procedures for that. There is a culture for incorporating, integrating them. Not so much so in developing countries. First, of course, there is a language barrier, both among faculty and administration in a university. So you have researchers who don't speak, say, Armenian. Of course, they need to use some services of the university administration. They need to communicate with faculty, and many of them can't. It's just they don't speak English, and that's it. You could say, well, how can a researcher in 21st century not speak English? But that's the reality. They don't. And the administration doesn't as well. So often they just find one person who does speak English, usually a young one, and that person becomes your contact point for whichever reasons, whether it is their responsibility or not. They unwillingly become your contact point for everything because they understand what you need and others don't, right? Then there are also cultural challenges, of course, because when you invite international researchers to your lab, their overall well-being, not just in the offices, but also at home and outside, their overall well-being is also something you should consider. And there are cultural challenges because if the general populace in the country is not used to welcoming many foreigners, except tourists, of course. But if you are not a tourist, then you need things which regular habitants need. So you need to use public services, you need to attend events and so on. And there are things that locals do differently. Challenges, there are also challenges related to the jurisdiction and bureaucracy. So basically, when you invite a researcher, there is a whole lot of bureaucracy and paperwork that needs to be done, and all kinds of contracts and this and that. And all of that is just fine-tuned for locals. So again, this is not only about developed countries. Say, when I worked in the US, there were many forms which I had to fill in and sign, where the address had to be a US address. So although it is meant for foreigners, but the form itself doesn't allow you to choose a country, right? So, and this is in the US, which is a developed country in many measures. And of course, it's harder in actual developing countries, right? So mechanisms are not well suited for international researchers, and you have to deal with them case by case. You have to then find key people higher in the ranks who can solve this in idiosyncratic ways, because the usual mechanisms just don't cope with it. And also public services, of course. There are some idiosyncrasies in public services. Say the healthcare facilities work in a certain way. You go there in a certain way, you register in a certain way. And for locals, this is like very logical because, again, they were raised in that. They haven't seen anything else. But for a foreigner, this may be very strange, and they may not guess what has to be done immediately, and there is often no one who could tell them, right? So, and these public services also have problems with languages, and they also have problems that they don't know how to deal with non-local residents or non-local citizens. So there are many challenges here, and although these aren't strictly speaking academic problems always, but again, so when you invite an international researcher, to some extent you also bear the responsibility for their overall well-being as an employer. So this is also your challenges as an organizer of international research group in a developing country. All right, so this is all challenges. These are all challenges I wanted to mention today, and I want to kind of finish this talk in a positive note. So, despite all these challenges, it definitely must be done. We definitely should establish and run mathematical research centers in developing countries, because there is a lot of talent, sometimes latent talent, in these countries. The majority of the world's population, the majority of humankind lives in developing countries. There is a lot of talent, a lot of potential for the humankind that needs to be developed, that needs to be given a chance. Okay, this is all I wanted to say today. Thank you very much.
Okay, Jirair, Abetishan, thank you very much for your presentation. So maybe it's time to make questions to Jirair. If someone wants to make a question to Jirair, please raise your hand. Try to unmute yourself. It's not a standard talk about mathematics, so maybe for people difficult sometimes to make a question, but I encourage. Maybe I can start, Jirair, because
yes, please.
You were very precise about especially two things, right? About resource challenges and about talent retention, right? Retention. So maybe you can come back to these 2 points again, and if maybe you can provide, summarizing the discussion, what we should do with respect to these 2 points.
Yeah, as far as talent acquisition goes, these are problems which are not necessarily academic in nature, and their solutions need not be purely in academia. So I would say one way of acquiring talent would be outreach beyond the walls of academia, to go to schools, to organize meetings with high schoolers, with their parents, spread information, spread booklets and whatever, try to deliver this mindset. Especially you can target the young minds because they are more flexible, that, once you have a good higher education, say, then you have more options. You don't necessarily need to become, say, a software developer to have a quality life. Actually, you can be also a mathematician and have a very fulfilling life. Maybe you won't have, an expensive car, as expensive as the one that your favorite, say, IT company boss has. But still, you will have a decent car. Okay, so this is, I think, the way to attract talent or to make the academic careers more appealing is the outreach beyond academia, first of all, because people need to understand that these career options are actually competitive in their own ways, right? So, and regarding the funding problems that I mentioned, here again, maybe there is a solution through outreach, but maybe slightly different nature. Say, if you can convey the message to the general populace that basic sciences are useful, it's harder to do usually with the population than with the government, because in a government, typically it's like the finance minister who decides how much money goes to which ministry and so on. These guys are very pragmatic. But if you can somehow, through years-long propaganda, convince your population that basic sciences, including mathematics, are important, with some examples of how they contribute to our quality of life and so on, then through democratic processes, the population will make sure the government allocates sufficient funding for it, because that's the more efficient way. The small number of academics are only a very thin layer of the society. They alone are usually unable to put sufficient pressure on the government. Governments usually act upon pressure. It's typical of governments. But the general populace can put sufficient pressure on governments to act, and that's one of the reasons why we have recent increase in research funding in Armenia, because the Armenian population began to demand it from the government. Before that, it's too hard. So any particular scholastic or professional, say, society is too small to put sufficient pressure. So that's how I see it, although there might be many more other ways of thinking it.
Okay, Jiraic, thank you. I think we have also one question from Sabrina Roscani from Argentina.
Yes, please.
Hello.
Sabrina.
Do you hear me?
Hello. Yes, I can hear you well.
Okay, thank you for your talk. I felt very identified with many things. So my question is, if you have teaching the university degree of mathematics in a developing country, and what is in your experience, or any other professor in this room, the best advice for a student, a brilliant, very brilliant student that is finishing the math degree, and you see that there are no opportunities or grade as you wish for him or her in your city or country?
Yeah, very good question, and actually a question that touches upon some painful issues. Indeed, it is usually that the very best, the top talent in a developing country is probably gonna end up outside of the country eventually, unfortunately. Now, that being said, what can you do? You can either try to stop it or you can help it. What I mean, if you try to stop it, then what happens, the student will probably do it anyway. It's just that the student will perceive their own country as an obstacle towards their progress. Whereas when their country is helping them to progress, if their country is giving them scholarships to go to the best universities abroad to study and really to grow as a professional, if their professors from their school, from their college, are helping them with their connections abroad to get to the best universities, they retain the feeling of belonging to that community, even though they may become eventually a professor somewhere at a Western university. They still have this belonging to this country, and they may one day return, or they may do something like a remote lab. They may be part of your research community in your country, either full-time or half-time. Whereas if you try to stop it, if you try to, by all means, keep them in the country, it's just gonna be destructive. They're gonna leave and never want to return. So that's what I believe. That's what I have seen on my own experience, and also historically regarding several famous scientists.
Thank you.
Sure.
Thank you very much, Sabrina Toscani from Rosario in Argentina. A very interesting question. Are there more questions for the Girair? Sohair, yes, please. Can you try to unmute yourself, Sohair?
Okay now?
Yes,
Okay.
now I can hear you.
So thank you very much for this talk. And there is this is a problem. I mean, we are now on a problem that it's like we enter into this domain, and after years we are observing these things that you mentioned. And I think in Africa, in many countries, things are similar. And then we are trying to do what? To solve a problem for whom? If those people don't understand that there is also now companies, societies, private societies that are attracting mathematicians, good talent, and removing bureaucracy, offering material stuff, and working in a very horizontal way in order to get solution. And now the solution, they will sell this solution. So if most of universities or institutions are for to deliver diploma, for people just to find a way to live, to be in life. And the story of innovation, creativity, is now going outside this what we call academic institution, because of now reason of the companies that are hiring. Like now, sometimes you see people talking at university about artificial intelligence, something like that. All the stories were not developed inside this institution, but outside. Now we are in the outside, observing these companies, and if this government refuse to understand, so they will have consequences in the future. And why we are putting our too much weight on us to solve this problem? Why?
Well, I guess you don't expect me to answer that question.
Yes, of course. I am just. This is the occasion to, because you are putting. You are saying things that now we are also thinking. You are like making the first element that we can now think about these things. Why are we doing research? Because we like doing this research? Is it personal now, or what? Or do we have some responsibility, some moral responsibility in our countries to do something, and we will have to fight against many obstacles? This is very, very complicated situation when we are.
Now, we are touching problems which are not necessarily typical of developing countries. I mean, these issues, these social, economic issues, they are also there in the most developed countries. These are hard questions to which I don't have answers, and I guess no one has right now. And one thing is sure, that the academic landscape, the way universities teach, the way universities work with their professors, this is all gonna transform in the coming few years, exactly for the reasons that you mentioned, because this competition with large companies, super large companies, who are, sometimes some companies are richer than individual countries. And obviously these companies are creating a field of competition, and this competition will force universities and governments to change one day or another. Again, unfortunately, as usual, good things will happen first in developed countries and then in developing countries. But hopefully at some point, at least, it will get also to developing countries. And regarding our responsibility, of course, whenever since Plato and Aristotle, there was something personal in pursuing academic endeavors, but the more attention and support we as researchers get from our society and government, the more responsibility we have to reciprocate against its responsibility for the society and for the country. So it's kind of a reciprocal thing. So the more support you get, the more responsible you feel.
The less support you get, the less.
Indeed.
I mean, okay. So what the? I mean, I appreciate very well this the title of the conference. The title, the title also of your talk. I mean, what can we do to create like a kind of atmosphere, or in order for researcher or this talent or something that we can keep moving, growing between these developing countries, which is because this is our first kind of problem, not the same problem as for the other developed countries. How can we contribute in getting results by creating this kind of international connection, and then sharing results, and then encouraging students, and the way that people can feel that they are contributing in doing something to humanity or something like that. Something practical, not only organizing conferences in these countries, but this is some kind of something that can be we think about in the future how to make this contribution by the tools we can have with what we have.
That's right. I can't pretend to have universal solutions to these questions. All I can say, what we are trying to do in face of all these challenges, we are trying to, to some extent, to isolate our team from some of the problems as much as we can, and other ways trying to collaborate with the interested, because in every, say, government or university, there are persons who understand and who are willing to help. If these persons are too few, then you are in problem. If there are sufficiently many such persons, you can do something.
Yes, you are right. What I have observed, I mean, when I discuss with colleagues in my country, and sometimes also in countries in Europe, and also in other continents, that the phenomena is the same phenomena is repeating itself. You find one of the best. The people that want to do something very serious in a department, you find 2 or 3 that are trying to have good results and to do publication in good journals, even in countries in Africa or other continents. And in each university, you find a very minority. And when we talk to them, they say the same words, the same phrases. They say, they feel isolated. They feel like they have problems everywhere. And even students sometimes don't come to take subject and be supervised with those. In contrast, they are very good. I mean, at the international level, they try to be at the international standard, but locally, they live in big troubles, and somehow, the word is like magic. Those people connect. It's like a community is created by those minorities. They like it, like if they recognize themselves, and then they connect, and this is what is happening, I think.
Okay.
Yes. But now, what those people, if they are connected, can do, or can, because also there is not a problem sometimes of the government. When I analyze some situation I am living, I will talk about my experience. What I discovered, sometimes when you talk with people at the ministry or the government, they answer you, what's happening at your university is not our decisions. This is rules, or this is practice that are local. It's your colleagues who are thinking like that, who are doing like that. So the problem becomes more complicated because it comes from the same how to say in French, le même corps, the same body. Is the body of the researcher, and the obstruction, or the how the way you say that, I mean, this, they refuse this, and then they become majority, and then you can do nothing.
Okay.
So the standard for thesis, they start defining the standards, their own standards, and this is a problem which is it's not in connection with the money, or with the. Sometimes the government said, I'm so far from these things. I'm not involved in this. in these things. It's yours. It's your body who is doing these things. So this is an extra problem also.
Indeed.
Okay.
Indeed.
Yes. Okay. Just okay. It's very nice to see how much reflection we have to take about the challenges that of doing mathematical research in developing countries. I want to say thanks to Jirair Abetisham for, of course, for sharing his experience, in particular for all the effort that he's doing co-directing the Armenian lab with Professor Michael Ruchansky in the Gender Analysis of Peace Center. I mentioned myself something about this in the opening ceremony about the perspective in Latin American countries. But then, thank you very much, Jirair, for your very nice talk.
It was my pleasure.
Sabrina also for the very nice question from Argentina. I think now maybe it's a good time to have a break, maybe 15 minutes break until the next talk. So see all of you and at 7:15 p.m. in Central European time. So at 19:15 in Central European.